Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
Today we are talking about the thermodynamic basis of astrophysics, so the lives and deaths of stars. And we've talked about this on the show a few times in the past. Usually we're looking at the observational evidence, like the sun seems to have a surface. How in the world does a ball of gas do that? And we've had scientists on the show who have argued against the idea that the star is a burning ball of gas, whether it's plasma or not. Seems like there's some condensed surface. There's other aspects of it that observationally tell us there's something else going on. But today, we have Steve Crothers, who is the mathematical detective, and Steve's coming at the gaseous sun from a very different angle. He's actually, in some sense, starting with the given statement that the star is a ball of gaseous plasma, and he's taking that idealized form of gas, the ideal gas laws, and prosecuting them through their logics to the conclusions that are drawn from astrophysics about, everything from how stars collapse and are formed to how stars make new elements in their core during fusion and how they die as black holes and white dwarfs. And so this is a very different way of approaching things from the basis of the theory itself.
But foundationally, what Steve has found is that even if you take the mathematics at face value, because the mathematics describe the stars, allegedly, he discovers that by doing careful analysis of the underlying principles of the thermodynamics that are at work inside of the equations, that they don't actually work. They violate themselves. They violate these fundamental principles of physics. And so Steve is like, these can't possibly be the equations that describe stars because they are internally self-contradictory.
And you might think, who cares if the star is a liquid or gas? And on one hand, you might be right about that, because science is often about just trying to make sense of nature. But we base all of our fusion projects on Earth on this understanding of how stars do this magic. So if we misunderstand it, we could be completely off on the wrong track with regard to developing this technology that could be super useful for exploring space and providing clean, sustainable energy here on Earth.
And although Steve's arguments tend to be deeply mathematical, we really sat down and we worked on how to present them to a wider audience because we think that it's unbelievably important for people to really understand the basis of why this doesn't work and what this means for all of astrophysics and cosmology.
But if you want to check out the very nitty-gritty details of that, check out these 3 papers right here, and you can get the full scoop and see if you can follow Steve's logic, because it seems like he has some really good points here.
So before we get to the conversation with Steve, there's 2 small orders of business. The first is that if you like what we do and you want to see more of it, come over to patreon.com/demystifysci. We meet with our patrons once a week. We do the Sunday Salon where we get together and we talk about sometimes the ideas from the podcast, sometimes things that people have been worrying about elsewhere in the world and want to put in front of this group of really curious, deep thinking, interested people. Joining the Patreon is what lets us survive because we cannot do this without you. We don't want to plaster ads all over this show. We don't want to have grounding sheets and weird, mysterious supplements being the backbone of this podcast. It has to be you guys. So come over to patreon.com/demystifysci. You can give us 75 cents a week, and that's enough for us. And we would really, really love to see you there. Second order of business is Paradigm Drift. We run this new segment where we give you, the theorists of the internet, 60 seconds to present whatever ideas you have about the world. It doesn't matter if you went to grad school. It doesn't matter if you have any kind of, formal education. What matters is that you have an idea about how the world works and you can explain it to us. And then we ask you about it. We ask you how you came up with it. You get a little interview with us before we send you on your way. So sign up for Paradigm Drift down in the description. And so if you want to present your theory, the next Paradigm Drift is going to be taped over Zoom August 4th at 7 p.m. Pacific. Sign up at the link in the description, and we will see you and your ideas at Paradigm Drift.
And I just want to add one more thing about Paradigm Drift, just to sort of, wet your whistle about the whole matter. Your goal is really just to convince us and the panel and the audience that there's something interesting happening here. if we find it interesting, we might and probably will invite you back without having to sign up to tell us more about it. And if we freaking love what's going on, maybe we'll bring you on to do an entire podcast about it. So it's really a pipeline to develop your ideas into something that really can change the world.
Excellent. Well said. I think that's all the business that we have for now. Enjoy our conversation live in person with the one and only mathematical detective of fundamental physics, Steve Crothers.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
We were just in Greece, and we were making these pilgrimages to all these ancient Greek sites and temples, and kind of trying to put ourselves in the shoes of the ancient Greeks a little bit, because I think it's not an exaggeration to say that a lot of what we do here, like in science, in trying to make sense of nature, is traceable back to the ancient Greeks. Like, they seem to be some of the first people who were really trying to rationalize nature, right? Because even if you go back to the Sumerians or something, they're keeping good star catalogs and records, but it's still very much about the gods, right? It's still very much about it's very mixed up with astrology and so forth. But the Greeks seem to be the first people, at least in the Western tradition. I don't know much about the East, but it seems like the Greeks are the first people who start asking questions about, how things materially give us the reality that we experience. They basically come up with physics as we know it. And so, who are the first people who were thinking about stars?
Well, of course, ancient societies had the worship of the sun, and it was all a sort of a fertility culture associated with the sun. Lots of primitive societies had this idea, and you got Ra with the Egyptians, rather, and Uta with the Sumerians and such. And it was all about this mystical aspect. But it seems to me that the ancient Greeks were the first to consider what the actual constitution of the stars is, or are. And so you had, for instance, some ancient Greek philosophers hypothesized that the sun was a hot stone. Others, it was some kind of burning material, because obviously there's heat and light coming off it. And so they started to institute the idea of, rather than worshipping it, what is it made of? What's it all doing? How can we understand what it's all about? So it seems to me that they were the first, at least in Western society that I know of, to look at the sun in that way. And of course, the other stars. So they started, I think, the scientific investigation of the celestial bodies.
Do you know if they had a sense of similarity between the other distant stars and the sun? Or was the sun in its own category and then the stars in the sky were separate?
I think that they sort of considered it the same in the same light. Of course, they thought that the stars sat on it's like a giant sphere of its own, and they were sitting up there. But this is speculation on a scientific approach, right? It's not, it's up there, we're going to worship it and make gods about it, and have various rituals that we'll undergo each year for the cycle of the seasons and this sort of thing, right? So it seems to me that the sun in particular, being the closest one, was the first one to hypothesize about on a scientific level, and to extend that then to the rest of the stars in some way, right? Bearing in mind that they didn't have telescopes to be able to explore the depths of the night sky.
I think they were generalizing, because if I'm not mistaken, I believe Aristotle, I think it was in meteorology, he talks about the planets as stars too. Like, every luminous object in the sky, including the sun and the planets, are all stars to him. It's just like a generalized term. So I think there was some generalization available, but and
It's kind of a crazy mental leap if you think about
It was.
to
It
be
was
able
a
to
huge
see
thing.
something like the sun, and then something that's so different, it's like a cold, distant nighttime star, and to kind of
Well, it's-
create a parallel.
It's so crazy that it gets buried for a while, right? So the alternative conception of reality, which is different than this material approach, is the Aristotelian approach, it seems like to me. And that's what the Christian church props up throughout most of the, what do you say, the first millennium, second millennium, really up until the Enlightenment. People are really have moved away from atomism, material approaches to physics. Everything is about forms and, you know, the ideal version of these celestial objects. And
I wonder if they didn't just lose the passion for trying to figure out how nature worked in the wake of empires falling apart and all of this just political and personal turmoil, where it's like the Greeks are at the peak of their arc when they're starting to think about the stars and creating mechanistic explanations for nature. And then that entire project just seems like it gets sidelined and people just get preoccupied by the burden of being alive for like 1,500 years.
Well, if you look at history, I suppose this is just my view, is that science waxes and wanes, of course, with political and imperial and kinds of approach, kinds of activities in the history of the world. So it's not immune from people who are not scientists, right? And of course, there are individuals who will work on it, but the basic theme varies, of course, with what society is all about. We look at the ancient Romans, for instance. They didn't really follow the Greek tradition after the Greeks declined. The ancient Romans didn't do a great deal of work in concerning science at all. They were great engineers, but they didn't really do much in the way of science. You don't know of any great. You don't have a great tradition with the ancient Romans as we did with the ancient Greeks. So it changes with various civilizations and who's dominating the world. So science is interfered with by all of these sorts of things. I think political and military. It's all in the end. It's empire building. So I'm not surprised that science over the years it's had periods of ascendancy and it's in considerations of the world and decline. So are we in now an ascending period or are we now in a declining period? It's a good question.
Yeah.
Depends which channel you're tuned into, I suppose. But yeah, so something really crazy happened. So when we talk about the history of astrophysics or just understanding how stars do what they do or what they are, why they look the way they do, it almost seems like the Greeks cared about this, at least a few Greeks, Thales of Miletus, Anaxagoras. Like there's some writings about these. We of course have the atomism, right, from Leucippus and who's the other guy? Democritus. So there is this discussion happening, but it disappears for like 2,000 years after that. That's crazy.
Yes, that's right.
And so finally, somebody gets the bright idea, I guess Galileo, to turn a telescope at the sky. And he's basically looking at the sun for the first time, from what I understand, and seeing and starting to like refine the idea of what's going on. What's the surface of the sun look like? It has these little dots on it. What's that all about? Well, maybe it's this sort of molten sea that has little clouds, and the sunspots are little clouds or something like this. And so for the next couple hundred years, from what I can tell, after Galileo, everybody takes it as if it's a molten ball of something with some sort of rarefied atmosphere. And they're arguing about whether it's, you know, a thin shell of molten or whether it's hollow, or there's all these like details. But for a couple hundred years, it seems like everybody's convinced that the star's a molten ball of some sort. This gaseous thing doesn't really appear until the 1800s.
That's right. Who knows why that the investigators decided on this? But in I think it was 1858, Herbert Spencer, who was a biologist of sorts, and he came up with the idea that the sun and the stars were gaseous. And I think it was in 1879 or thereabouts that an American scientist by the name of J. Homer Lane decided that they're not only just gases, they're an ideal gas. And so then the kinetic theory of ideal gases, as it was then and still, was applied then to this idea. Oh, it's an ideal gas. We can treat it as an ideal gas, and that's been the foundation of the theory of stars ever since. So it's been elaborated on, of course, in all this time. But the basic fundamental idea, or the basic idea, hasn't changed. It's a gas, and they can be treated as an ideal gas.
So let's take that apart, though. Like, I wanna try to get at the heart of why people change their mind about it. And I have a theory that I'll throw on the table, and I would love for you to react to it. But actually, Nasti and I have developed this in conversation over the years. But it seems to us like something changed in the world around that time, right? There was the success of engine building for this first time, which was all based on ideal gas laws, combustion. You started seeing artificial lighting based on gas lamps for the first time. So the technological landscape of the day was very amenable to the idea that gases could be these luminous power orbs, right? People were seeing that in their daily lives. It kind of reminds us of when people today talk about brains, they always talk about computational power and the processing power of people's minds and stuff. And that's because computers are the revolutionary technology of our day. But back in the late 1700s, early 1800s, mid 1800s, it was the engines, right? It was these gaseous compression systems that were the state of the art. That was the high tech of the world. That was what the smart people were thinking about.
True.
And so we wonder, how much of that background, what would we call it? Just the spirit of the zeitgeist, the spirit of the day. How much of that was just hypnotizing the scientists as well? Because that was what you study. That's the way you think about systems if you're a high-tech scientist back in, the 1800s.
Well, that's true, I suppose. We had James Watt and the development of steam engines of all sorts, not just locomotives, but all sorts of steam-driven devices. And so we're talking about heated water just becomes vaporized, and you've got high-pressure gases and such, and hot gases. So I suppose it's a good hypothesis that these sorts of technological advances influence the scientists as well as to how they're going to approach the analysis of the physical world around them. It's a good idea.
And they were having a hell of a time figuring out how to power the stars too, right? So there was something else that happened, which was, so the thermodynamicists, so I believe it was Helmholtz and Lord Kelvin had proposed essentially that there's this compressive power generation system, right? So basically like a diesel engine, the star squishes itself and gets hot and glows. And, that was fairly convincing at first because that's how everybody understood engines to combust as well. And so this heating mechanism was okay. But then, at the same time, there's all these revolutions in geology and archaeology, and people are starting to realize that, hey, the Earth's been around for millions and millions of years. Like, we just can't explain everything that we see in these fossil-struck records without having way more time than you would have available to you with this compression mechanism. So they basically calculated that the sun would burn itself out in a matter of, tens of millions of years under this compression mechanism. And they were stranded without like a good explanation for how it would work. And so I think that the remaining champions at that point of a molten star, they seem to be leaning on these radioactive explanations. And then at the same time, people, I forget, it was a woman actually. What was her name? Cecilia Payne. Basically convinced everybody the stars are made out of hydrogen and helium, mostly hydrogen. And so they're like, well, they can't be doing that radioactive stuff. The only thing that's left, and you mentioned Spencer, but also who did the phase diagrams at the time? Was it Stevens? Who am I thinking of? Well, anyways, they basically were squeezing hydrogen as hard as they could. And no matter how hard they squeezed it, they didn't get it out of the gas phase into anything approximating a liquid, right? And so if stars are made out of hydrogen and the stars, squishing hydrogen doesn't turn it into a liquid, of course they didn't have access to the kind of shock pressures that we can do in laboratories today, then all they're left with is a gas, basically. And they have to make it work somehow. which eventually leads to this gaseous fusion stuff in the subsequent century, right? Where people try to solve this problem based on gas laws still. But they basically can't move from the gas paradigm into anything else because they don't have a way of powering the stars with liquids at the time. And so there's something there about these unsolved mysteries that, yeah, they don't really know how to solve them, but the alternative, that it is some sort of a molten fluid, seems completely against the evidence that they're looking at the time.
It's an interesting thing that the ancient Greeks never considered the sun and the stars to be gases at all.
Right.
It was condensed matter for them, right? Whether it's stones or liquids or hot burning stones, it's all for them condensed matter. Then it changed from condensed matter to gases, right? And now recently it's changed again from gases back to condensed matter. And James Jeans was a proponent of liquid stars, and he didn't have and when he discovered that. Or learnt that hydrogen seems to be the main component, he didn't have an energy source for it, so he abandoned this idea. And so the gaseous model predominated. And Eddington rightly pointed out that it's probably nuclear reactions in the gases, in the stars rather, that is the source of energy. But Eddington maintained that these reactions were able to be maintained within gases. He even claimed that the gaseous stars 2,000 times the density of platinum exist. Well, a gas at 2,000 times the density of platinum, it should have been a problem then. Scientists should have objected to this idea and seen that there was something wrong. But nonetheless, with Eddington's authority, and this is the problem with scientists citing authority all the time, which I often do. Oh, we can't question this famous scientist's idea, and so we'll adopt it. And
I think they just didn't have anything to jump ship to.
And they didn't have anything, that's true, but they proceeded with the idea of gaseous stars, oblivious to what they were doing in terms of violations of already established laws of physics, like in thermodynamics, right?
We will get
and the
to
kinetic
that.
theory, which we'll get to later, yeah.
Well, so do you think that in part it was just that the mathematics of the ideal gas law were so convenient that it was possible to put a pin on the question and then just move on to doing other things, which is now turning your attention to, like, well, how do stars form? How do they die? And that way, if you have the equation for how they're maintained, you're able to just keep moving without getting stuck on the same question.
I agree. The mathematics seems to be the favoured means of investigating nature now, rather than experiment and observation, and applying the laws of physics that we know that we've developed from those experiments. So mathematics has now usurped the position, and it started with that, I think, as well, with the ideal gas law, as you say, and the ability to use mathematics to try to understand the universe, right? But I don't think that's the way you understand the universe at all. Mathematics is not, the universe is physical. It's not a mathematical object. So yeah, I think that's got merit, and that could be one of the reasons why.
Can I just fill in one gap that I realized we might have left open for people who are listening? So the thermodynamicists, Helmholtz, Kelvin, proposed that, the star is sort of powering itself like a diesel engine, this compressive thing. And that doesn't totally work out. And Eddington doesn't know how the stars are powered either yet. He does, like you say in a lecture, suggest maybe there's some nuclear processes. And eventually, I think it's like Beth, is it? Some other scientists developed the fusion stuff later. But what Eddington does supply is this idea that to counteract the sort of collapsing stuff, there's this radiation pressure that works and opposes it, right? So he sort of saves the age of the stars without actually solving the problem of how they power themselves.
That's true. Radiation pressure is opposed to the so-called gravitational attraction. But you've got a gas, which they're treating as ideal, right? But there are no gas. In a gas, there are no gravitational forces between the particles of an ideal gas. All the ideal gas theory and kinetic theory is based on a container where the gas particles they exert no forces except when they collide elastically with the walls of their container and with each other. So there are no forces between them. So if you're using now the ideal gas law, which they are, and you now give gravitational forces, allow gravitational forces between the particles of the ideal gas, now you're in violation of the very theory that you're applying, the kinetic theory of an ideal gas. And this is the problem that leads to violations of the kinetic theory, because that's a straight up violation. And it manifests also in violations of the laws of thermodynamics, which have been determined by experiments here on Earth. Right. So
were they aware of these problems at the time? Was it a compromise that they were making? Does Eddington discuss any of this in his writings, or is he worried about some of these like apparent issues
No.
with? Yeah,
no. They
like the container, for instance.
Yeah,
that seems like an obvious one.
It's an obvious one, but the trouble is they're applying these theories outside their domain. Right. So if you want to talk about an ideal gas, you've got to remember you have to define volume, temperature, mass, and you can't define volume if you haven't got a container. You can't define the radius of a spherical object of a gaseous object that doesn't have a container. And we know from experiments on Earth that gases have a shape of the container. They don't have a shape of their own, and they have a volume, which is the volume of the container they fill. And all the experiments on gases that led to the kinetic theory of an ideal gas are performed on contained gases. Sometimes you might have a piston or something to change the volume and all. That's where you get the volume of the gases change. We observe what the temperature does. We observe what the pressure does, and then you can either push the piston in or pull the piston out. And of course, this also relates to the laws of thermodynamics, because we're talking about temperatures. So whenever you've got a temperature involved here, of course, you're in the domain of thermodynamics as well. And the ideal gas law, of course, relates temperature to pressure and volume, and the mass of the system.
And so is the reason that the container is so important for the ideal gas law simply because gases can't actually be studied in any kind of reasonable way unless they're inside of a container because of the fact that they just dissipate?
Well, that's right. If you let a gas out of a container, you open the box, or it's containing it, for instance, and the gas will expand into the surroundings. So without the container, what's the volume of the gas to just expand? Part of it's expanded. Okay, well, what shape is it? What's its mass? What's its volume? How can you determine that without the container?
Where does the pressure come from?
Yeah, where does the pressure come from? We've just said that the pressure in an ideal gas is due to the elastic collisions of the particles with the walls of the container. Well, walls of a container, that's important, and when they collide with one another. But the collision of the particles is not causing the pressure. The pressure in the gas in the container is due to the collisions with the wall. Right. So all the particles collisions are just a manifestation of the pressure that's produced by the collisions with the walls. So the idea of a gas out in space having a pressure, well, this is a violation of the ideal gas law. You can't define the pressure of an ideal gas where you don't have a container. So the stars, the gaseous models of the stars, straight up don't have a container.
Well, gravity kind of is brought into the fold to be this mysterious force that pulls on the gaseous particles and attracts them to each other, and so kind of acts as a quasi-container.
Somebody might be listening to this and be like, well, the atmosphere of the Earth is held on with gravity, right? And that's a gas. So how is that different?
Well,
is it settled that it's held on just by gravity?
The first thing is the Earth's surface is condensed matter. It's a wall, right? And the gravity is acting on the gas, the body of the gas, the bulk gas, right? But the particles of a gas, and remember we're talking of an ideal gas to model these things, there are no gravitational forces between the particles themselves. But the gravitational forces between the particles and Earth is different. That's not it's not gravitational forces between the particles themselves, right? And so in the Earth being a wall, you've got a real area against which you can have the particles collide and produce a pressure. After all, in physics, pressure is force divided by the area. Force over area is pressure. If you don't have a real area, you've got no object for the particles to collide with to produce a pressure. And so the gaseous model of the stars thinks that they've got pressure in the absence of container with a fictitious area, or an area that they don't even consider, because what causes the pressure of these stars? Well, they try to now say, well, the gravitational forces pull the particles together. They're only gas particles. Right? There's no condensed matter in this model. So the gas particles pull on one another and cause the gas to condense into a spherical shape and form a star. But again, there are no gravitational forces. There's no other forces, in fact, between the particles of an ideal gas. There are no forces except, as I said, with the collisions with the walls of the container and themselves. And without the walls of the container, you have no pressure.
Okay, so another question. The Laplace nebular hypothesis for the formation of stars and solar systems predates the attribution of the ideal gas law to stars.
Yes.
And so it seems like the ground is set by a previous theory for gravity to have a sufficient role in this, where they're not thinking about the fact that there's a missing container because they're already operating within the parameters of a theory that says that it's possible for a nebula to collapse to produce the stars in the first place.
Right. What motivated people to think that they could have gravitational collapse of a gas which has no container and it's out in space, which should be expanding? Gases expand into space. If you take a box of gas and you take it into orbit, for instance, and you open it up outside the space rocket or whatever you're in, what's the gas going to do? It'll expand, and it doesn't matter how much gas. The argument is we've got lots of gas, and there's so much gas up there, it magically now becomes gravitational. Well, it doesn't matter how much gas you've got. You can have a huge container of gas and open up the lid, and out goes the gas. And why does it expand? Because the gas particles have kinetic energy. So they will go out and follow their trajectories, or not trajectories because that's a gravitational thing, but they'll move away from one another under their kinetic energies. So there's no gravitation involved here. And remember, we're always talking here about an ideal gas law, which has a certain setting. And if you're going to now use this theory outside its setting completely, now you're into grounds or areas where the gas theory does not apply. And that's the fundamental problem. So they forget about this. They're looking at how they can produce pressures with radiation pressure, like Eddington, against the gravitational contraction of a gas, where the gravitation of a gas is a fallacy. Right.
I've seen this story change even in modern times, like in my lifetime. I've seen it sort of like they've started to realize that most of these stellar nursery nebula are not gravitationally bound. Like they actually are sort of drifting apart, the gases. And so they have started to really focus on, these pressure waves from supernova and other things that could result in these overdensities necessary to nucleate a star, because I think it's become more and more apparent that it's an untenable feature that balls of gas would just kind of fall together. Have you noticed that? I just feel like astronomers I talk to have kind of stepped away from that accretion idea as much as they can. Like they're pointing more at these other overpressure mechanisms.
I haven't seen actually any real move away from a theory of gaseous stars.
Not gaseous stars, but just I'm talking about like maybe we're getting ahead of ourselves with the formation models a little bit, but
right.
And I do want to make sure that people who are listening understand that we're going to go through in just a minute the birth, the life, and the death of stars, and how the story we've been telling for 100 years is rooted in ideal gas laws. So it can't be overstated. I mean, we should perhaps really make it clear that the ideal gas laws really are at the heart of stellar mechanics, even into today.
Well, something that I'm trying to figure out right now is whether or not they were using ideal gas laws for like Kant and Laplace when they were formulating the original nebular hypothesis. Because if the star forms at the center of some kind of gaseous nebula, there is some frame that allows for that to happen.
This is the earliest modern story of how stars form, and it's congruent with ideal gases. But did it come from ideal gases? Did the nebular collapse model come out of, or was it there? to begin with. Is that what you're saying?
Yeah, like I think that the nebular hypothesis predates the ideal gas law, because nebular hypothesis is 1755.
That's right.
Ideal gas law is 1800s. And so they've already got this model that they like a lot. And so I feel like it's maybe even just a convenience to be able to apply some mathematical frame to a model that they already like and want to be able to give better legs to. Does that seem reasonable?
I don't know. What do you think?
Well, I suppose it's got some, that idea's got merit to it because they want to have a model. They were trying to develop a model that they could use mathematics with and try to construct a theory of the formation of stars and the internal constitution of stars. But in so doing, they've forgotten the experimental basis upon which the fundamental physical theories that they're using. So, as I said, if you look at a gas, no gases compress themselves, right? No gas compress itself. We know that to compress a gas, you need two things. You need some kind of containment and you need some kind of external agent. Now, a bicycle pump is a very simple example. So it's a piston and you push on a bicycle pump, you've got walls, you've got an external agent, you're the external agent if you're pushing the bicycle pump piston, and then you can push the gas into a tire or whatever. Now, if you think about the gaseous stars, there's no external agent in gaseous stars. In the case of the Earth, there's an external agent. The Earth and the gravity of the Earth is external to the gaseous system itself. So, but the gas itself can't compress itself. But in the theory of gaseous stars, the idea is that the gas compresses itself. They call this self-compression of a gas gravitational collapse because gravitation is the mechanism that they want to use for the gas particles to collapse. Right? But the gravitation of the gas itself, how is that an external agent to the gas itself? Right? It's not an external agent to begin with. Because that would be within the system.
If the star wasn't gas, like just if there was a huge object made out of, I don't know, metal or something, could it push on itself gravitationally? Could it do work on itself still? Is this a problem with it being a gas, or is this a problem with an object doing work on itself?
Well, well, that's another issue. No system can do work on itself. If you take a system which is a finite region, if you like, whether it's in reality or in your imagination for analysis, all the systems are finite in size, right? And you isolate a system maybe from its surroundings, and the surroundings are all systems, which are by definition finite, and they interact with these other systems, or the system under investigation. And any systems that don't interact with the system under investigation are irrelevant. Right? So, and what's the system itself? The system can do work on other systems, or other systems can do work on the system under investigation, and energy can be transferred in other ways like heat, for instance. And so no system can do work on itself, right? For instance, you want to now take this system to do work on itself, to compress itself. It can't be done.
Is that happening though on Earth?
No, it's happening in the theory of gaseous stars.
No, but like, isn't there, like, I don't know. I have a hard. I'm sure you're right. I've always had a hard time visualizing this because if I think about like the surface of the Earth bearing down on the mantle underneath it, there's like a lot of compressive heat generated, right, as a result of this.
Yeah, but the Earth is condensed matter.
Oh, no. That's what I'm trying to separate out. Is this a problem with a gas, or is this a problem with a system doing work on itself? Because if the Earth can do work on itself,
Okay, dumb question.
Do you see what I'm saying?
I thought that partially the heat of the Earth had to do with its gravitational interaction with
it's very complicated.
sun and the moon
and it's
and
formation residuals and all this
right.
stuff. It's
So
complicated.
it's like, is it heating? Because okay, so hold on a
Is
second.
the Earth doing work on itself? I guess that's my question.
Well, when you're talking about work, it's either the system does work on its surroundings or the surroundings does work on the system. Right? We're not talking about things inside the system.
Because doesn't that make a perpetual motion?
Yeah,
well,
yeah.
it is cooling off.
I get it. I think the Earth can do work on itself, is what I'm trying to say.
Well,
Like, I think it can
I think that
cool
Steve's putting
off.
an axiom down,
Yeah,
which
yeah,
is
yeah.
the fact that like a system axiomatically cannot do work on itself because it requires an external actor to do work on it because
And I'm just trying to separate out how much of that we have the gaseous discussion going, and now we have a thermodynamic discussion of whether a system can do work on itself. And I'm just trying to make sure that no system that I can reason through can do work on itself, not just gaseous systems.
so I just arrived at perhaps what might be a useful question. Why can a system not do work on itself?
This is a definition of a system. You look at what a definition of a system in thermodynamics, which I mentioned earlier, right? It's an isolated region. It has finite volume. It has finite mass. And you either have real walls or you have some imaginary walls, but it's isolated from, or separated rather, because the word isolation has some other context in thermodynamics. So we'll say, in fact, separated from its surroundings. And the surroundings, by definition, are other systems. Right. So what are the systems doing? One system interacts with another system. Right. So if you do, one system will work on another system, or it can transfer heat to a system, or the system you're talking about can do work on other systems. So it's either having some systems work on it, or it does work on other systems. So this is what's meant by no system can do work on itself. Right. Things can happen inside a system. Right, but that's not what we're talking about.
But like a system is defined as an equilibrium.
Not necessarily an equilibrium,
no, okay.
Right? We talk about...
How do you draw the lines between one system and the next? You know, like if I wanted to say the atmosphere of the Earth is a system and the Earth is a system, and therefore the Earth can pull on the atmosphere.
Well, that's right. We've got two systems here. One's the gas, and one's the Earth, right? And here now you can have gravity because the Earth is got gravitational forces and it acts on the gas of the atmosphere. And so you don't have the gas itself or the atmosphere itself compressing itself. The gas itself is not compressing itself, right?
So I think that I have in my head the image of a thermodynamic work function, right? Which is that like you have a closed cycle of the state of the system. As you go into like a higher energy state, then you dissipate your energy and then you return to the initial conformation and then you can kind of go back up to the peak.
You're talking about like a heat engine.
Sure. And I'm like, for me, that's exactly why a system can't do work upon itself. Because if it could, you could have a perpetual motion machine.
That's right.
And so since we have never found a perpetual motion machine and all attempts to do so have failed, I think
probably shouldn't expect them in nature.
We shouldn't expect them in nature, and I think that this is where the axiom comes from, because if you think through, like, what does it mean to do work? It means to take something that's in a low energy conformation, to raise it to a higher energy conformation, and then to allow that to dissipate and then return back to the initial condition from which you can raise it again to some higher level. And if you don't have something external that can raise it to the higher level, then you can't do work. Like, it's not self-contained. Is that reasonable?
But also there's, when you're talking about a cycle, right, you have reversible processes and irreversible processes. Some systems can go, you can do a cycle, right? You know, the Carnot cycle, for instance. But then you have other situations where you can't do a reversible situation, or a reversible. There's no cycle. You can't. It's not reversible. In other words, so there's a very clear delineation made between these sorts of things or systems in thermodynamics, right? So, but for the purpose of our discussion of gaseous stars, right?
What's an example of an irreversible system? Like something like the combustion of petroleum or something?
Or take a say you've got a container and you've got a partition and you've got or a little membrane or something and you've got gases on two sides, right? And now you burst the membrane and the gases quickly intermingle. Well, that's a system that can't be reversed, right? It's a process, rather, that can't be reversed, right? But if you have a piston in a container with our gas, back to that again, which is how all the scientists determined the kinetic theory of an ideal gas with experiments in this way, you can move the piston in and out. Now, if you do it really slowly, you can, because in thermodynamics, it doesn't really matter how long it takes to change from one state of equilibrium to another state of equilibrium. We're not really concerned about how long that takes in thermodynamics, because we're really talking about ultimately equilibrium between different points of equilibrium, right? So if it takes a long time or a short time, thermodynamics is not really concerned with that. We want to see what changes when it's changed from one scenario. For example, we change the volume with our piston, and we keep the temperature. Say we got the temperature rather, and we got pressure, and so we know there is a relationship between the pressure and the volume and the temperature, which has been determined by experiments, right? So we want to now change the volume. Okay, we change the volume, and we examine then what happens to the pressure and the volume of the in the temperature, or we can either make the volume greater or less. And we move the piston in and out with an external agent, right? We can see what goes on there, okay? So that gives us a way of determining then, which is done by experiment, the relationship between what I've called thermodynamic coordinates, because the pressure, the volume, the mass, the temperature, these are thermodynamic coordinates for this system. Now, thermodynamic coordinates can depend on the system. So we have, for example, surface films, and here the surface film is treated as an area. So we don't have a volume here, right? And then you can have a string or a tension in a wire. We don't have here. We have temperature. We have the length of the string, and so we don't have really volume of the string. It's not involved, right? So you have to be careful when you're looking at this, what your system is, as to determine what are the thermodynamic coordinates for the system, right? And so all these thermodynamic coordinates for your system are related to one another. And that's what we try to analyze in thermodynamics, for instance. When it goes from one state of equilibrium to another state of equilibrium, how do these thermodynamic coordinates change? Right? So we look at that. And how long it takes is usually not involved.
I mean, I can see the appeal for why using ideal gas laws would be nice if you could pull it off to explain everything that's happening. Like it's a very simple, ideal gas laws are something you learn in high school. You know, it's a simple relationship. It seems easy to manipulate. These variables are controllable in a simple system in a laboratory. It would be really wonderful if we could apply them to the stars. But it seems like I think I just finally grasped for the first time totally why, like, the fundamental difference between a burning ball of gas model of the sun and the Earth as far as gravity is concerned. Because in the Earth, the atoms are all holding on to each other. They're condensates, right? They're knitted together in different bonding regimes, whatever, covalent, ionic. Basically, the atoms are all knotted up together, however you want to look at it. But in a gas, by definition, the atoms are bouncing off each other. And if you could go ideal gas law, they're bouncing perfectly off of each other. Isn't that right? They're perfectly elastic, right?
Perfectly elastic.
So they never dissipate any of that. They're just pure bounce.
That's right.
And so the model on its fit, I have a hard time believing this wasn't a problem for people in the 1800s even. Like, that just...
Yeah, because, okay, they understood thermodynamics well enough to be able to say that you need to be able to have something external that does work on a system. So how, given that understanding, right? Like, these are the people that invented the theory.
Yeah, these are smart people.
So, how is it that they get around it? Is it because my intuition is that our understanding of gravity is incomplete to this day, even, and so it acts as this kind of magical glue that's able to do things, because we look out onto the world and we're like, well, clearly it has been done. there's a burning ball of gas in the sky, ergo
Gas?
it must, well, that's right, but they're looking at it and they've gone through the process of, well, it can't be liquid because it's hydrogen and helium. We can't make hydrogen and helium into liquids, ergo it must be gaseous, and if it's a gas, we have mathematics that work for it, that are the ideal gas laws, and the external work must be delivered by this magical substance that is gravity, which is that which does work on the system and so allows it to work upon itself. Like, this seems like
It's
the
like a
train of thought.
concession. It's almost like, it just almost feels like they just gave up. Like, maybe everybody in the room realized it was a problem, but in so much as gravity also seems like magic, well, why not just have like a little more magic in the story?
This is an issue I've never been able to understand, how you entertain these ideas. But if you think about the ideal gas law, right? PV equals nRT. Pressure, volume is equal to the number of mole, which is effectively a measure of the mass. R being the universal gas constant and T the temperature. Now, in this situation, what are our thermodynamic coordinates? It's P, V, N, and T. Right? So it's mass, volume, pressure, and temperature. R being a constant. It's not a thermodynamic coordinate, right? So you've got this equation, and they hypothesize it's a gas, but then they forget that equation comes from the experiments with containers. So they take the equation itself. Oh, we've got volume. I'll call that volume. Okay, we've got a volume of a star. And we've got the pressure. Oh, the pressure. They don't think that you can't have a pressure if you don't have a well-defined volume, which is determined by the container. And so just looking at the equation itself, and then with the hypothesis that the stars are gases, they start to apply, this is what seems to me, they start to apply the ideas of the relationships between these coordinates by forgetting what its etiology is. So now
these people probably also, these astronomers who are doing this, they'd probably never worked with gases in laboratories. Is that reasonable to assume? Like, these are not the same people. Well, with the exception of Helmholtz and Kelvin, like, most of these people are probably not experimental chemists.
Well, it's true that many of these are theoreticians, right, who don't do experiments, but that I don't think's the issue.
I'm just trying to figure out how you make this leap. Like, it just seems so absurd.
Yeah.
It seems like some first year students in the auditorium might raise their hand and be like, "Excuse me, professor, like, I'm not sure that this makes sense." And like,
but I think that Steve's making a really good point. It does have pressure. It does have volume. It does have temperature. Like, they're arguing about the fact of like, well, how do we keep it from collapsing? Like, clearly it's exerting pressure.
Yeah.
So as I said, you take the equation, you've got PV equals nRT, and your hypothesis that it's a gas. Now you've completely forgotten about where PV equals nRT comes from. So without thinking about where it comes from, you say, oh, well, I've got a pressure and I've got a volume, and if I hypothesize that the star is a gas and it's got this volume, and what will be the pressure if it's got that temperature? And so now you can find relationships between these coordinates, right? But that's all you've done. It's completely outside the context of physical reality. It's now just based on this equation. Now, that seems to me how it's sort of got into the idea of gaseous stars. You just take this equation, as I said, which comes from a certain context. Now you're outside the context, and you now use the relationships between these coordinates, right, and just say, well, I've got this ball of gas. I hypothesize of a ball of gas. It's spherical, so its volume is what? 4/3 pi r cubed. Okay. Right? But how do you have the gas spherical? Oh, well, it's got gravity. And we're going to put gravity in, and the gravity keeps this relationship between PV equals nRT. Now you're straight away in violation of the kinetic theory without realizing it, because you're only concentrating on the equation and the relationships between them and hypothesizing ways and means to make sure that you've got the right shape so you can calculate a volume. Yeah, if it's a sphere, its volume is 4/3 pi r cubed. Yeah, well, sure, but have you got a spherical container to put that in? No. So if you haven't got a spherical container, where's the pressure coming from? We know that the gas produces its pressure by the collisions of the particles, in the ideal gas law especially, with only elastic collisions with the walls of the container. That's where the pressure comes from, right? So now you've got a spherical gas without a container. The equations that you're using are for a container, but you forget about the container. You've just got the equation. Oh, well, I want to hypothesize that it's spherical, and I can calculate its sphere. If I know the radius, I know its volume is 4/3 pi r cubed, and that's the volume I'm going to put into this equation. But by doing that, you're completely outside of physical reality because you've taken that expression away from its setting, where all experiments are done in relation to containers, right? No experiments on this development of the ideal gas law were done without containers. For instance, how do you know the pressure and volume and relationships between that and temperature if you don't have the container? How did the people who developed the kinetic theory of ideal gases develop the relationship between pressure and volume and temperature without a container? They didn't. They couldn't have. Right? But in this idea of a gaseous star, there is no container. So they have to have some way, a means of to give it the shape that they want. We want a sphere. Okay, well, it must be gravity. It must be gravity that's pulling the particles down.
Yeah,
well, as I said,
who's the first person to suggest that? Is that Eddington?
The first person to talk about
Gravity doing the containing.
Well, that's a good question.
Isn't
I don't know
gravitational
I don't think it was.
collapse the nebular hypothesis?
I think that's what we were driving at
That
earlier.
could be the case, but we're talking here in total absence of condensed matter, right? If you have condensed matter, now you've got some gravitational, you can invoke some gravitational forces, you've got condensed matter around, right? But we're now talking here pure gases, right? This is what it is. And the gas is supposed to now gravitationally collapse. I call that self-compression because that's what it is. And it exposes what they're really talking about with gravitational collapse, right? It's compressing itself because it's a gas, right? And there's no condensed matter.
I call it the
in this.
popped balloon putting itself back in the balloon. The gas,
True.
yeah.
If you pop a balloon, it's a good example. You pop a balloon, what happens to the gas? It spreads out, but it's not going to collapse again and compress itself. That's what, as I said, collapse. But that doesn't happen, and it's a fact of reality, right? Show me a gas in any laboratory that's compressed itself. You've got no container. Well, how do you isolate this gas if it's not contained?
I put this
and
in
then
front
study
of,
it. It doesn't happen.
We've asked so many astrophysicists about this on the show, and every single one of them falls back on this sort of Jedi mind trick where they're like, well, if it's big enough. That's what they always say. They say, well, you can't take laboratory, you can't think about the balloon because this is a really big balloon. And if the balloon's big enough, then gravity can do it. And I never know, my mind doesn't even know what to do with that.
Okay, well, this is a typical example of what happens in cosmology and astronomy, right? The laws of physics now no longer apply to their theories. So if you now jettison the laws of physics, you can make up anything you like. And that's essentially what they do.
When did that start? That's so unique and bizarre. Like,
it's bizarre.
From both of us came up in medical biosciences, when we started to get into all of this astrophysics and cosmology and everything, it was pretty shocking the sorts of assertions that get by that you could never make in a standard biophysical system, for instance. You just can't say these kinds of things. Nobody would take you seriously. You can't just say something's different like, oh, I'm studying this cell and it does this thing, and it doesn't do it anywhere else in the universe, but it does it inside of my cell. Like, nobody would go with that. It's such a strange. Can you point to a moment in history where is this it? Is this idea that gravity can collapse a ball of gas the first time when something that's clearly contraindicated by experiments here on Earth is accepted to be the case just because of scale?
This is, as I said before, this is how astronomy and cosmology do things. They completely ignore the physics that we've developed on Earth. Now let's think about what astronomy and astrophysics and cosmology are. They are, well, astrophysics is actually a better term because it says astrophysics, stars and physics. So you take the laws of physics and you apply it to the stars. Where did you determine those laws of physics? Experiments here on Earth. Now, if you're going to say now those experiments here on Earth and those laws of physics that we've developed here on Earth through those experiments no longer apply, and we can do what we like out in space. So now we have gases that collapse themselves, they compress themselves. We have gravity between the particles of the gas. Gases don't now expand. And what's the argument? Well, they're really big. What has that got to do with gases? It doesn't matter how big your container of gas is. To open the lid, the gas will escape. Now, you're in outer space. Well, open the lid, the gas will escape. Right? And remember that they're always modelling it as an ideal gas. And those ideal gas laws are also being determined on Earth. So this is how cosmology, astronomy, and astrophysics get around problems with it, such as this that I pointed out to them. Oh, well, we don't have to obey these laws of physics. It's way out in space, and it's really big.
Yeah.
This is so illogical and divorced from physical reality that one can not understand how any scientist would entertain such an idea. But it's become, over time, something like an ideology. Right? So you have this ideology instead of paying attention to what physics and science is really about.
I do want to add something here, which is that when you go and you start digging around and asking the internet, do scientists still use the ideal gas law for the sun? The answer is no, not really, because the ideal gas law requires there to not be interactions between particles. Now we know that the sun is a plasma, and so clearly there's a lot of interactions. And so I think that it's worth noting that the ideal gas law was a convenient approximation when in the 1920s they were trying to figure out like what the sun was made of and how it was operating, and that there do seem to have been some modifications to it where the ideal gas law in its pure form is no longer applied, but it doesn't mean that people have changed their mind about the structure of the sun not being a gas, because now it's a gaseous plasma with other considerations and interactions and everything else.
The fact of the matter is, without the ideal gas law, they have no theory. So this idea that they are approximating it, this is just not real, not true. Because without the ideal gas law, they have no theory of gaseous stars, right?
I think they have no equations of state. They have
none.
They have no fusion. They have no basis for the fusion mechanisms that they propose. Like, I've been down this rabbit hole before. I literally had a student one time stand up in my lecture hall and be like, "I heard that the ideal gas laws aren't used anymore," and I was kind of like, I was a little scared for a second. I'm just like, "Whoa, all right." I don't know what this guy's been reading, but last time I went and looked at the standard equations of state for the stars, they were built on ideal gas laws.
Built on an
so
ideal
I
gas
asked
law.
this kid, so I'm like, because I'm like, maybe he knows something I don't know. Maybe there's been some work, like people have changed things. You never know, like what's happening. I don't know. Maybe he read some article that I didn't read. And I go, "Where'd you hear that?" He goes, "Straight face, YouTube comments section." Because I'd been sharing some of these PR videos with my class, right? And so there's of course some knuckle dragger in the comments section who's sitting there trying to shout these things down. And I was I remember I won't say the kid's name, but I was like, "Listen, man, like you can't. You should check things out that you read in the YouTube comments section."
Without the ideal gas law, they have no theory of stars. Their whole theory of stars is based on ideal gas law. Without that, they can't compute anything.
And that's what I want to go through in the back half of this conversation, because you've taken three pieces of the puzzle and you've kind of assumed, okay, what if we do use the ideal gas law? Like, let's just assume, let's take the astrophysicists and try to use these ideal gas laws and see if we can process them logically and arrive at the same conclusions about things like the accretion, things like the powering, like nucleosynthesis inside of the stars, the ultra compact objects at the end of stellar evolution. Like, can you actually arrive at those conclusions even using the ideal gas laws? Let alone the fact that there's problems with using ideal gas laws. And you seem to come down on the conclusion, you come down definitively on the side of those aren't reasonable conclusions, even if you use the ideal gas law.
Of course not. First, the ideal gas law is inappropriate. That's the first thing. The second thing is, to use it in this context, you're in violation of the kinetic theory, right? So they're incompatible. The other thing about it is that it also leads to violations of the laws of thermodynamics. I'm going to give you a very simple example of cosmology before we talk more about stars. there's an equation for the temperature of a black hole. Now, this was proposed by Stephen Hawking, and it's related to what's called Hawking radiation. And it's supposed to be a black body spectrum that's radiated by black holes at this temperature. And to put it simply, the temperature is inversely proportional to the mass of a black hole. So it's so the constant of proportionality is actually made up of numbers, like pi.
So it gets
2.
cold. It gets cold as it gets big. Is that what you're saying? Just for the
It's inversely proportional to the mass. Right?
us normies out there.
So let's take this example. It's very simple, right? T is inversely proportional to the mass. So let's write that equation really simple in our minds. T, the temperature, is equal to K, which is a constant, divided by the mass. Now, this K is actually composed of other constants and numbers, like pi and a number, a numeral, and some physical constants, speed of light, the Planck's constant, right? So we won't complicate it with dividing up the constant into other constants and numbers, right? Physical constants and pure numbers. So we'll just put them all together. We got T is equal to K, which is a constant made up of other constants all multiplied together, divided by the mass, right? Now, there are two things to see here. If you take a brick in a kiln and it's in equilibrium, so that means the temperature is now settled and now it's in equilibrium state, which is what we often talk about.
The whole brick is the same temperature.
Yeah, the brick's the same temperature.
Yeah.
Now, in your mind's eye, take a knife or some kind of cutting device at the same temperature as the bricks, cut the bricks in half. Does the temperature of those two bricks change? No. Now you take those two pieces of brick and put them back together. You're still in the kiln. Everything's at the same temperature, so we know we're in equilibrium. You put them back together. Does the temperature of those two bricks now, when they're put together again, does the temperature of that reunion change? The answer is no. Anybody who's worked in a kitchen knows that they cut their cake out of the oven, cut it in half. The temperature of those two pieces are the same. You put them back together, and they're the same, right? Now, with Hawking's equation, the temperature is inversely proportional to the mass. So if you take two masses, right, at the same temperature and put them together, that means you've now doubled the mass. But because it's inversely proportional to the mass, right, you've halved the temperature, right? So this doesn't happen in physical reality. It's a violation of what's called the Zeroth law of thermodynamics. What does the Zeroth law of thermodynamics state? It's this very simple statement. If you have three objects, we'll call them A, B, and C. And if A is in thermal equilibrium with B, and A is also in thermal equilibrium with C, then B and C are in thermal equilibrium with one another. Now, take B and C, which are in thermal equilibrium by this law, and put them together. Are they still in thermal equilibrium? Of course. There is no change in the temperature because they're already at the same temperature because they're with A, as I said, A with B, A with C, put the C and B and C together, they're still the same temperature. So this is the zeroth law of thermodynamics. So when you take two objects at some temperature, they can be the same or different, and put them together. Now, if they're at the same temperature, nothing changes. If they're at different temperatures, you're no longer in equilibrium, and you wait for equilibrium to occur, right? And where's the final temperature? Somewhere between the lowest temperature of one, which one had the lowest temperature, and the one which had the highest temperature, somewhere in between there. But is the temperature that's final the sum of the two temperatures that you started with? Say one's 100 degrees and the other's 120 degrees, and you put them together. Is the final temperature 220 degrees? No. What do cosmologists do? And they add temperatures. Right? Not only that, what does Hawking do? You double the mass, so these two objects that we've just put together have masses. Say they're the same mass, right? We put them together, we've doubled the mass of the object, right? The temperature doesn't change, they're at the same temperature, right? What does Hawking's theory equation do? You take two black holes, because they're black holes, right? We'll assume for the sake of argument that black holes exist. They're actually fantasies, but we'll assume for the sake of argument. You take these two masses, they're the same, and they're at the same temperature. The two black holes coalesce, right? So, strictly speaking, the mass now is doubled, right? We're not going to worry about gravitational waves falling off it and taking away some of the mass. We'll keep it real simple. The two masses come together. Now the mass is doubled, but they're at the same temperature, right? Is the temperature of this final black hole, which is now twice the mass, is the temperature the same? By the zeroth law, yes, they're the same. It's the same as the two parts that you started with, right? What does Hawking's equation do? You take the two masses together and the temperature is now half of the temperature that you started with the two objects. That doesn't happen in reality. That only happens in, I have to say it, it's a fantasy land, right? Now, if you now halve the mass, so let's think of it hypothetically that we can cut this black hole in half. Don't worry about their non-bifurcation theorem. It doesn't matter for our purposes. You cut the mass of this black hole in half, it becomes 2. Now, it's got a temperature. Now it becomes 2. They're at the same temperature, right? Okay, if they're at the same temperature, they should be at the same temperature by the zeroth law of thermodynamics. Now, what do you do with Hawking's equation? Just look at, remember, T is equal to K divided by M. Now, we halve that mass. So we've chopped it in half. So we've then got two masses. Each one's got a temperature, T equals K over M. But that mass is half the original. That means you've doubled the temperature of that mass by cutting it in half. This is absurd. Yet that silly equation is etched into Hawking's tombstone in the floor of Westminster Abbey, where they've buried his remains next to Isaac Newton or close to Isaac Newton, right? But it is a nonsense equation.
But people might say, "Oh, well, black holes are special, like you already said. They're pretty wild and amazing and everything." What about stars?
Now we come back, but we come back to, well, what is astrophysics? It's the application of the laws of physics determined on Earth applied to the stars, because you can't go to a star and do an experiment on it. No one's done an experiment like that on a star. You can't. So, and the laws of physics are what we have here. It's the same with cosmology across the board, astronomy, astrophysics. It's all part and parcel of the same sort of thing, right? We're looking at the cosmos beyond the Earth's surface. But you don't have any laws of physics that you've invented, or not invented, just determined by experiments on stars. No. All the laws of physics and chemistry and the like are determined on Earth. So astrophysics is the application of the laws of physics to the stars. Let's not forget that. Because the important thing is here, what is the context?
It sounds so legitimate on its surface.
So now it looks, but when you go into cosmology and astronomy, they have these violations of the experiments and the laws of physics determined by experiments on Earth. And then they say, well, our theory doesn't have to abide by that law. We don't have to conserve, for instance, the energy and momentum of a closed system. Or we don't have to have a container for our gas. Or our gas is so big that it can compress itself. Show me experiments on Earth, because that's what physics is, an experimental science. Give me your proof of experiments on Earth that can do the things that you say is happening way out there in the cosmos, right, with your hypothetical or your theoretical structure of things like stars and right.
They seem
galaxies
perfectly comfortable with the exceptionalism of what they're proposing.
Yes.
Like we recently had this conference in Portugal, and some mainstream cosmologists there, and they just seem perfectly comfortable with the idea that weird things happen in space. Like, it's kind of bizarre that that's the twist that it takes. It's almost like you would think that if you're having a conversation with somebody and you're like, hey, that we've never seen anything like this happen before in a laboratory. We can't do anything even close to this. In fact, it's the opposite of what we actually see. You would think they'd be like, yeah, maybe that is a problem. But for some reason, this is a class of thought that thrives in the exceptionalism of the mechanisms they're proposing.
I actually think that the attitude that I saw most at the conference was, that can't possibly be true.
What can't be true?
So it's like, if you, in conversations with mainstream cosmologists, like, for example, we were talking about the CMB, whether or not the CMB has been measured at L2. And
oh God.
Right, I know. I hear the hounds of hell. But basically, when you tell someone that there's good reason to believe that it hasn't been measured, they're like, that's not possible, you're wrong. And so it's not even, like, when you say something about the fact that perhaps the mathematics of the equations of state and these, like the Hawking radiation and all of these pieces aren't
thermodynamically sound,
they're like, that's not possible. That's just not possible. How could that be possible? Like, I don't see them engaging with the ideas on the level of, no, space is totally exceptional. They're like, it's not possible that we're wrong.
I see the exception. I don't know. I see that, especially with the mass thing with these astronomers who are like, well, it's just big. Once it's big enough, then it can start to collapse. And you're like, well, where does it become big enough? And then they get into like the virial theorem, and it just becomes this like
Okay.
this kind of like inundating quantitative.
What's the
They have a
virial
theory.
theorem?
They have
Okay.
a theory for the size of the gas. This comes back to what's called the Jeans mass, right?
Okay.
When the mass is this big, according to the Jeans mass and the Jeans length, which is the radius essentially of the uncontained gas cloud, which is spherical, right? The Jeans mass is critical. Once it reaches the Jeans mass or goes beyond it, it will collapse. In other words, it will self-compress. But the problem is, when you examine the derivation of the Jeans mass, what do you find? You find that the Jeans mass, named after Jeans, right?
The last liquid theorist.
Yeah, you find that they violated two things: the kinetic theory of an ideal gas and the laws of thermodynamics in deriving the Jeans mass. So this Jeans mass is a fallacy. But they rely on the Jeans mass to say to you, oh, since it's big enough, it will collapse. It's quite ridiculous in that.
Do you want to break that down a little bit? Like, I think we're probably like deep enough into this conversation that if people are still hanging around, they probably want to hear the details of that.
Okay.
So what goes wrong in calculating the Jeans mass?
Because they use the kinetic theory of an ideal gas. Remember, this is all gases. So they're using the kinetic theory of an ideal gas. Eddington says himself, if we can treat the stars, it's an ideal gas. He even says they must be an ideal gas. Chandrasekhar does the same. We can treat the stars as an ideal gas, and all the forces can be, he just says this in his book. He says, all the forces except gravity can be eliminated. We don't, because it's an ideal gas. Yeah, but in an ideal gas, there is no gravity. So why is he retaining gravity? Well, they've got to have some mechanism for their cloud of gas, hypothesized cloud of gas, to collapse and form a star. So they keep the gravity and use the ideal gas law. And then you've got a problem, because you can't combine gravity with the ideal gas law. We know already that one of the premises of the ideal gas law is that there are no forces between. Well, gravity is a force. There are no Coulomb forces. Coulomb's electrical charge forces. There are no forces except when the particles collide with the walls of the container and themselves. That's important, right? Now, as I said, they get rid of the container and they take this equation and they're playing around with the equation itself. So when they do this, they use the ideal gas law and they use and they violate the ideal gas law, and that leads to violations of the laws of thermodynamics to derive in the derivation of their Jeans mass. Then they take this Jeans mass, which is invalid, and say to you, oh, well, once it gets big enough, the Jeans mass will tell us it'll collapse.
Hey guys, quick interruption to remind you that this podcast is entirely paid for by listeners out of the goodness of their heart. That means we don't have any sponsors, we're not selling you anything, but we need you to come over and consider giving as little as 75 cents a week to make sure that we have the time and resources to make more and more of this program. So I'll see you over at patreon.com/DemystifySci. Is there any way that, like, without doing like a full mathematical proof, that you can explain how the mass is brought in some way?
Yes, I can explain to you basically this. Well, the first step is the application or the misapplication of the virial theorem, which relates the kinetic energy of a gravitationally bound system with the potential energy, the gravitational potential energy, which again rises its head. Now, if you have a number of masses, condensed matter, they're gravitationally bound, and you can write an expression for the gravitational energy of that system. But with the ideal gas, since there's no gravitational forces between those particles, they're not gravitationally bound. Nonetheless, the astronomers, they treat the gas particles as like they were condensed matter. They are condensed matter particles or objects, and apply an equation for the gravitational potential energy. As we see, that's a violation straight away of the kinetic theory of an ideal gas. Now, the virial theorem relating the kinetic energy of this system, of their uncontained gas, with the potential energy, which is they've given the gravitational potential energy to, they combine the gravitational potential energy with the kinetic energy of an ideal gas. So now that involves temperature. Right? By the equation that we saw before, the kinetic energy is equal to 3 on 2 kT. And that's for the total number of particles, because the gas cloud is made up of many particles. Let's call the number of particles of gas N. N's the number of particles.
Let's throw these equations up really quick.
Yeah. So by taking the kinetic energy of all the gas particles, right, and then using that in the virial theorem with their gravitational potential energy of their cloud of gas, mistreating it as a gravitationally bound system, they combine the temperature of an ideal gas with gravitational potential energy again. Then they solve for a temperature. Now that temperature equation is intensive on the left and it's not intensive on the right. Then what they do is that they replace the number of particles N with the number of particles of the mass, mass of the gas, and they solve for the what they call the Jeans mass, which is the maximum amount of gas that they have to have for the initiation of self-compression.
Maximum or minimum?
Oh, sorry, you're correct. The minimum amount of mass that's needed for the gas to compress itself. Now, when I said it's an equation, it's actually an inequality, right? The mass has to be greater than a certain amount, right? Now, when they solve for this mass, they solve it for the Jeans mass, and you have Jeans mass on the left. Remember, we've combined the potential energy with the kinetic energy of an ideal gas, again, which is forbidden. But by doing that, then they ultimately solve for the mass M of the system. That is the minimum mass that they need to form a star from a gas cloud. Now, when you look at the equation for the Jeans mass, the mass on the left is extensive. Mass is always extensive. But when you look on the right of their equation, you find that it's depending on two thermodynamic coordinates, the temperature and the density, initial density, right?
Is that the rho naught?
Rho sub zero, yeah. So that means the right-hand side is intensive, because if you take the product or the quotient of two intensive properties, it remains intensive. They're both homogeneous degree 0. So on the left you have extensive, homogeneous degree 1, and on the right you have intensive, homogeneous degree 0. Now, even though the units on the right come out to be mass, they are not thermodynamically balanced. That's a violation, right, of the laws of thermodynamics. That means the Jeans mass is invalid.
Okay, so in one of your papers, you do make this comment about the fact that it is possible to change an extensive property into an intensive one through a mathematical operation. Like you can take something like mass and volume, which are both extensive. But mass divided by volume produces density, which becomes intensive.
If you take any two different extensive quantities, like the example you just gave of density, mass divided by volume. Mass is extensive, it's homogeneous degree 1. Volume is extensive, it's homogeneous degree 1. But the mass is in the numerator and the volume is in the denominator. That means the overall homogeneity of it is 1 minus 1, that's 0. That means the right-hand side, which is the quotient of two different extensive properties, is 0. So if you take any two different extensive properties and take their quotient, you will always get an intensive property, right? And the density is a typical example, right?
But you're making the case that they don't do this here. And actually, hold on, before that, is there some way of going from an intensive property and modifying it to become extensive?
No.
Okay, so this is a one-directional process.
That's right. Because the only way you can make some intensive property incorporate it into an extensive expression is to multiply it by some extensive property.
So if you take density and you multiply it by volume, then you end up at mass.
Correct. Because density is homogeneous degree 0
Mm.
and multiplied by volume, which is homogeneous degree 1, the total is 0 plus 1, that's 1. It's extensive. And then the mass on the right now, that's extensive. It's balanced.
Okay, so is there anything that you can do to temperature to reformulate it into an
No.
extensive property?
No, temperature is fundamental.
Mm.
You can't divide or multiply temperature. As I said before, the only way you can get an overall expression using an intensive property, and you want say, for argument's sake, you want to end up with an extensive coordinate, something that's maybe say the product of temperature. Well, you take an extensive property and multiply the temperature by the extensive property, but you can't turn temperature itself into an extensive property in any way because it's always intensive. And if you take two different intensive properties and multiply them, the homogeneity is 0 plus 0, that's 0. Or if you divide them, you have 0 minus 0, that's 0. So it doesn't change the intensity or the intensivity rather of that product or quotient.
Okay, so why is this something that isn't more known, right? Because like all of us had physics, we went through thermodynamics, and this matter of intensive and extensive properties and the relationship between them never showed up.
And most people seem to be completely unfamiliar with
They
it.
are.
When
Most people aren't familiar with it.
And yet you open your papers with a statement that some people have proposed that this should actually be the fourth law of thermodynamics.
That's correct. That's correct. But if you read the textbooks and the literature of the cosmologists, the astronomers, and the astrophysicists, it seems that they are entirely oblivious or ignorant of the fact that thermodynamic equations must thermodynamically balance. Why? I don't know. But it's the truth of the matter, as examination of their works prove, as my papers explain. So their theory of gaseous stars, almost everywhere they mention a temperature, they derive a temperature. Their temperature is in violation because it makes temperature non-intensive. Similarly, they make masses non-extensive, which means that those expressions are violations of thermodynamics and they are therefore certainly invalid. And this covers everything they've done with accretion, everything that they've done with thermonuclear reactions in the stars, everything that they have done with the gene's mass, the Chandrasekhar limit, their formation of, or their theory of white dwarfs and neutron stars. It is everywhere. It's so bad that there's nothing that will survive from their theory of gaseous stars. Nothing.
I can see why you're not a popular guy at cosmology conferences.
And it's the same as I said with cosmology. I gave the example of Hawking's equation. That's just one. And there are many others. That's in other papers that I've written, one of them which I wrote with Pierre Robitaille. Dr. Pierre Robitaille wrote an article on the Unruh effect and Hawking black holes and all. And so the Unruh effect is in violation of the laws of thermodynamics just in exactly the same way as Hawking's equation. So the Unruh effect is nonsensical. It's invalid, and there's nothing that they can do to, none of these people can to salvage their theories without changing the laws of thermodynamics ad hoc. And that's what they often do when they're cornered on these issues. You've made a mistake here. They do one of two things. They either go silent, or they say, well, we don't have to obey the laws of thermodynamics. But you do. Right? See, for instance, they also say we don't have to obey the laws of conservation of energy and momentum of a closed system. Yes, you do, because that's experimentally determined. Just because you have a theory that violates these laws doesn't give you the right to just jettison the laws of thermodynamics or the laws of physics generally so that you can have your theory that violates those laws. Astrophysics, astronomy, cosmology, they have no experimental basis other than the physics that we determine on Earth. So if you now use laws that don't have any basis in experimental physics on Earth, you're not talking physics. You're not talking any science. And so the whole theory of gaseous stars is dead. It will never, ever survive this because the laws of thermodynamics are fundamental. So you cannot just go off and decide you're going to change the second law of thermodynamics or the zeroth law. You can't do that. That's experimentally determined. Your arguments are not, and they're in violation of it.
All right, so thus far we have talked about the problems with treating stars as ideal gases, but we've also entertained the mathematical, theoretical argument that if they do start with the assumption that ideal gases can be used, can we process that logically and arrive at the conclusions of the standard model? And your work so far that we've talked about on accretion seems to answer definitively that that's not possible due to violations of basic thermodynamic balances. So the character of these thermodynamic expressions, you end up having to make assumptions like putting together two hot pieces of cake makes, a colder piece of cake or an even hotter piece of cake. It makes no sense. And so these astronomers have either been unwittingly unaware of the thermodynamic balances or they've ignored them because it was inconvenient. But we've arrived at mathematical expressions that violate basic thermodynamics. And so now we're going to think a little bit more about how stars sustain themselves over the course of their life. We've talked about how stars are formed. Let's talk about nucleosynthesis. So the basic process by which all of the atoms in this room are said to have been made is in the hearts of different stars. And the standard model has it that because this story requires different pressures and densities to create different elements, you have to have several generations of stars leading up through explosions and recombinations to give us all of the elements. And it in some sense reinforces this story going back to the Big Bang because you need these generations of stars. And each generation is only capable of generating the elements specified by its temperature, density regime, which brings in mass, volume. Basically, all of these attributes that are specified by ideal gas laws. And so you've written this second paper that we'll link down in the description, where you are arguing, again, that this story of the different elements being synthesized based on different density and temperature regimes is on its face problematic for reasons we've discussed plenty concerning the appearance of stars as gases. There's problems with this, but also that the logic itself, even assuming they are ideal gases, falls apart because of the thermodynamic balances that are resulting as you process this ideal gas assumption and come up with this story. So I hope that has at least opened the floor. And of course, the details of how this falls apart are quite elaborate. So I was hoping you could give us an example of how this intensive, extensive mismatch has misled the theoreticians with respect to nucleosynthesis. And, there's multiple examples in this paper, but maybe we can just check out one of them for right now.
Well, the first thing is, as you said, there's a number of steps involved for the determination of a nuclear reaction rate in stars. And the first step is that the astronomers determine a classical temperature, and in the lead up to a temperature that will initiate nuclear reactions involving charged particles and collisions and such. So what they do is they, again, use the kinetic theory of an ideal gas, and instead of applying it in relation to gravitational potential energy, they do it to Coulomb potential energy because we're involving charged particles here. So they end up giving now a temperature to Coulomb potential energy. There's two problems straight away, as we know. the left side of this equation is temperature, so it's intensive. The right side is not intensive, so that's a violation of thermodynamics. And the second thing is Coulomb potential energy, like gravitational potential energy, has no temperature, can't contribute to temperature, so the whole expression is nonsensical. Then they build on this nonsensical equation and could generate even more nonsensical equations. So because the temperature from the classical form is too low to be able to generate the nuclear reactions that they want, they invert quantum mechanics. So they, via the momentum wavelength relationship, right? So effectively they get another temperature, which they call the quantum temperature. And this quantum temperature is larger than the classical temperature. And from this they conclude, well, we have enough temperature now to cause nuclear reactions in gases.
Are they adding these temperatures together, or
No,
what's going on here?
No, this is not an addition of temperatures. This is a modification of the classical temperature, because the classical temperature that they've calculated is too low for the production of what they think is needed for the initiation of nuclear reactions in gases. Right? Assuming, of course, that you can get a nuclear reaction by just raising the temperature of a gas, which is not true. So they modified this using quantum mechanics, using the relationship between momentum and wavelength. And so they eliminate radius in terms of this, because it's really an impact parameter. So they then get a temperature as a result of which they call a quantum temperature, and that's higher than the classical temperature. And they say, well, this one's high enough. This means we can cause nuclear reactions in gaseous stars, because the quantum form of the temperature gives us a sufficiently high temperature to initiate nuclear reactions in gases. But the problem is that quantum temperature is the temperature on the left, again, that's intensive. It's homogeneous degree zero. But on the right side of this equation, there are no thermodynamic coordinates at all. They are all constants. So they've related the temperature to something that's nothing but constants, a combination of constants, which is a nonsensical expression. In terms of mathematics, well, it's homogeneous degree zero on the left, and it has no thermodynamic character whatsoever on the right, so it's unbalanced. So a temperature assigned to a whole collection of constants is quite ridiculous.
And so basically the takeaway is that there's not a solid model that can actually explain how nucleosynthesis is happening. And so as we've been having this conversation, I've been slowly coming to the realization that the impact that your work has is that it reopens astrophysics to being a discipline that actually has a lot left to figure out, which is really exciting, because when somebody who's a young scientist comes into astrophysics right now, they inherit all of these equations, they inherit all of these principles, and it seems like everything has been done already and has been more or less figured out. And so now the job is to just look out at the sky and to catalog, how many of each object there are, and to fit the objects that already exist into this map of various equations. And so what you're saying is you're like, well, no, the equations that are used to make this case, that we understand how stars are capable of producing these heavy elements, actually aren't functional. And so we don't actually know how this is happening.
Can I go one step further? I think that it actually, maybe more than anything else we've talked about in this conversation, this one matters the most, I think.
Why?
Potentially.
Okay.
Because the holy grail of engineering is the development, harnessing the power of stars on Earth. This is at the forefront of so many different topics with engineers, right? So fusion technology, whether it's for space travel, whether it's for clean power here on Earth, it matters to people. And the approaches, generally speaking, to producing fusion power in our technological applications depend on an inherited understanding of how stars do this magic. And if we misapprehend that, or if we arrogantly assume we know everything there is to know about it, then we're going to just keep throwing money at a system that's bound to fail or at least be ineffective at the bare minimum. And so most of the fusion systems are these gaseous plasma tokamak type reactors. What are they called? These plasma focus devices. They're based on trying to create really high temperature gaseous plasmas and focus them in such a way that you can force these collisions to happen, because this is more or less how people have come to understand stars. And so I think that this one is really, really technologically important. At least it could have a huge impact on the future of our race, our human race.
Well, I agree. Without the nuclear reactions in gaseous stars, all these projects to produce controlled nuclear reaction pies in the sky. They will never work. You've got the ITER project in France, funded by 7 countries, and the cost of it is estimated to be even to blow out to huge numbers of dollars, or even some estimates are up to 60 billion can be built on this contraption. And it really is a contraption, because the theory of nuclear reaction in gaseous stars is certainly false, and they're trying to build this controlled nuclear fusion on the basis of the theory of gaseous stars. So it's never going to work. You'll see reports fairly recently too about how they're making these wonderful this wonderful progress in the goal of controlled nuclear fusion, and all these reports only talk about how long they've confined a gaseous plasma within their contraptions, right? So it's up to how many minutes? 16 minutes, 22 minutes or something. It was the last report. So big deal. It's not going to do anything. Even if they manage to do it indefinitely, it will never work, because the whole theory upon which they are basing it is the gaseous model of the stars and thermodynamic reactions in stars, which is completely false. So none of these approaches will ever work. There has to be some other way to pursue the objective of a controlled nuclear fusion, but it certainly won't be via gases, and it certainly won't be the ITER project, which is just a waste of money. All of these projects are a waste of money. So they're just employing people for no real purpose.
And then, more from a pure natural philosophy standpoint, this really instructs how we understand the lives and deaths of stars, right? So when we look up at the sky, we see some weird stuff. And one of the weird things we see is that there appear to be these really dim but really hot stars. We call them white dwarfs, right?
Yes.
Really dim but really hot, which is weird. And honestly, that you have to sit with that for a second. The problem with the gaseous model of the stars is that the only way to make something dim and hot is to shrink it. And
Correct.
So, of course, the name itself sort of betrays the assumption that these are really small. Of course, if you have a different material basis for the stars, which we really aren't even getting into today, but you actually have other ways of dimming something without it shrinking. But if we take the standard model seriously for a second, and we try to create one of these ultra compact, tiny little hot stars, a white dwarf, based on the ideal gas laws, once again, we run into thermodynamic problems with the logic processing those assumptions. And so you have another paper about these white dwarf stars and ultra dense compact objects in general. These neutron stars suffer the same fate. Black holes suffer the same fate. What can you tell us about the logic underlying these conclusions?
According to the astronomers, for white dwarfs, there's a relationship. The mass times the volume equals a constant. So in other words, if you rearrange this simple expression, you've got the volume is inversely proportional to the mass. So you increase the mass, you reduce the size. That's another one. The other thing is that they conclude, which is remarkable, is that they say that the density is proportional to the square of the mass. Well, that should be another trigger to show that you've made a mistake. But nonetheless, they take that as serious. But the reason why these come about is because they're violating all the time the kinetic theory of an ideal gas and the laws of thermodynamics. And in relation to the Chandrasekhar limit, which is I've explained in detail in my paper, and it's really too complicated to present here.
But in case people aren't aware, the Chandrasekhar limit is essentially how this point you reach when you try to cram too much mass into too small of a radius or too small of a volume, really, where these two pressures we talked about earlier, the radiation pressure and the gravitational glue that holds it together, the gravity sort of takes over at some point because you got just too much stuff pulling. And so the gas starts to collapse on itself, and you end up in one of these terminal situations like a black hole or a neutron star, where the materials collapse to the point that you have to actually theorize new forms of matter in order to even make sense of how so much stuff could be in one place.
Well, yes, they invoke a thing called degenerate matter, and the Chandrasekhar limit sets the maximum mass that a white dwarf can have before it becomes unstable and it'll collapse into something like a neutron star or a black hole. Well, neither neutron stars nor black holes exist, and white dwarfs, although they exist as stars, they're not dwarf. It's got nothing to do with ultra dense compact objects. This comes from the gaseous model of stars, which is replete. It's amazing how many violations of the kinetic theory of an ideal gas and the laws of thermodynamics are involved in the determination of these fanciful objects. So much so that I don't think astronomy will have anything left after this demonstration that the whole theory of gaseous stars is false, other than maybe that the sun is big and round and shines and the earth goes around it. Because everything else about their stars is false. They have absolutely no valid theory of the stars. The gaseous theory or the gaseous model of stars is certainly wrong, and it won't hold up anything, right? Whether it's by radiation pressure or otherwise.
Well, that's the thing is, if you start with this gaseous assumption, the only thing you can think of, the only thing in your toolbox to make something hot and dim is to shrink it.
Yes, that's what they claim.
If you have actual material structure to the stars, which is obviously what we're all sort of, that's the alternative, that you have a material structure. It's some sort of metallic substance that has actual interactions on a stable basis between the atoms, so there's a lattice of some sort. If you have that, now you have to apply all of the diverse material properties that we understand optically emerge from different lattice arrangements in that material. So you have the ability to change the atomic structure, the relationship among the atoms in the lattice, to produce different levels of brightness, right? So, we see this all the time on Earth. Like you can take carbon, right? And you can arrange it in a certain pattern, say sort of like graphene or something, and it becomes optically opaque. You can't shine a light through it. Or you can arrange it in a sort of cubic situation so that it looks like a diamond, and you can propose to your wife with it, but you can shine a light right through it. In fact, it's such beautiful light, the way it refracts and everything, that we value these arrangements of carbon completely differently than we do soot or just carbon dust, basically, right? But it's still carbon. But you don't have to apply that logic to a gas, because there's no real stable long-term relationship among the arrangement of these atoms. And so we just assume that we don't have to think about these kind of optical emissivity issues that change with the material structure. So the toolkit for creating a dim object in gases is extremely limited, whereas the toolkit for creating a dim object in condensed matter is much more diverse. You can actually start to think about processes that might be rearrangements of that architecture that could result in the appearance of these dim but still hot objects. They don't have to be small, in other words. And so this really changes the entire landscape upon which all of this plays out.
That's right. as I said, the gaseous theory of stars has no valid scientific basis. So gases are not the structure of stars. What's left is condensed matter. So what form of condensed matter would it be? Well, Dr. Robitaille has argued that the form is metallic hydrogen. And the reason is because the metallic hydrogen has a hexagonal planar structure, which is similar to graphite. And the other thing is, of course, only condensed matter emits a thermal spectrum. Now, when you look at the sun, for example, you have a thermal spectrum. In other words, it's got a Planckian distribution over the frequencies. And it's a scientific fact that no gas has ever been observed in the laboratory to emit a Planckian spectrum. Gases do not do that. They emit in bands. Now, no amount of line broadening by any means will cause a gaseous band emission to miraculously or mysteriously or magically change into a thermal spectrum. Yet when you look at the spectrum of the sun, it is a thermal spectrum, right? So that is of itself demonstration that the sun is condensed matter. Now you look at the stars, they are in similar fashion. They are emitting thermal spectra. So that's telling you that the stars, the sun, are all condensed matter. Bearing in mind, of course, that we've just shown that everything about the gaseous model of the stars is false for violations of the laws of thermodynamics and the laws of the kinetic theory of ideal gases. Right. So
all of this is a totally understandable mistake in the 1800s, from what I can tell. Like at the beginning of our discussion, we were talking about the history a bit, and I was saying that they were trying to develop these phase diagrams for hydrogen, and they couldn't get hydrogen to go into a liquid no matter how. And I think I said it was Stevens. It was actually Andrews who did this work, trying to show that, is there a way that we can get condensed matter out of squishing hydrogen? And they couldn't do it. They didn't have access to the sorts of, diamond anvil experiments or the shock compression experiments that we do today to produce liquid metallic hydrogen. So they didn't know. But what's really unfortunate is that we haven't really updated our priors on this problem. Right? So we're still working off of a basic 1800s understanding of the phase diagram of hydrogen when we treat stars like they should be gases. This seems like a simple and easy to correct mistake. The problem is the fallout from this mistake impacts so many different disciplines of astronomy, but also, fusion science, things that we've put millions and millions, maybe billions and billions of dollars behind, perhaps misguided to the extent that they're 150, 200 years out of date in their approach. And that's perhaps a little bit embarrassing and unfortunate.
Something that I've wondered about as we've been having this discussion is whether or not there's a problem of mathematics of comparable function for fluids and condensed matter as for gases. Because we've made this case over and over again that the utility of the ideal gas law is that it is relatively straightforward and tells you a lot about the system that you're studying. And in many ways, it seems to have emerged from our discussion that the reason for that is that an ideal gas is so simplified. You've removed a lot of the Coulombic forces, you've removed any of the gravitational forces. You're able to work with something that is truly ideal. And so it allows you to create this body of knowledge because the computation of the product is relatively straightforward. From what I understand about the mathematics of condensed matter and fluid mechanics, they're quite complicated. Is that perhaps part of the reason that there's this reticence to switch, because all of a sudden it makes it much more difficult to understand?
I don't really think that really is the case, because the mathematics that's involved in the gaseous theory of stars is itself quite involved. And I don't think that that's really the problem. I think it's an acceptance of a model that has been around for quite a while. Remember, it started in 1858, and it's been built into a massive edifice where many people have got a lot of skin in the game, as they say, right? and so they're very reluctant to admit to anything that shows that this theory that they have is not just got a few mistakes in it, but is absolutely wrong in every
It's
aspect.
so heartbreaking to consider that this process by which we create knowledge is so deeply flawed by this human ego of not wanting to go back on something that we've been doing for decades.
Well, I don't think it's just ego. I'm sorry, I
Yeah, go
interrupt
ahead.
you. I don't think it's just ego. I think it's actually a survival instinct. You have a situation where people's livelihood, their jobs, their families depend on maintaining their preeminence in this discussion, and that's a really pure vetted, like, academics live purely off of their ascendance in some reputational hierarchy. So the worst possible thing you can do is piss off the people who are the esteemed authorities in your domain. That is it's literally suicide. Like, you're basically taking the bread out of your children's mouths by contradicting the people who are putting the bread on your table.
Okay, so that's true, but those same esteemed authorities get together at conferences all the time, and ostensibly, they want to figure out how all of this stuff works. Like, if you're the guy who's in charge of the fusion project, you should want to have a way of producing sustainable fusion first. And so the crazy thing about this is that the model that we've built suggests that there is better information out there for producing a more effective fusion reactor on Earth, winning that race, becoming the most esteemed person in the world because you've created this technology. And yet there's still some kind of reticence to jump ship and go in that direction, even among the most esteemed people that have all the resources. Like, that's crazy.
Well, some people seem to be working on the new model, and I don't know if people in general are aware of that, but there are some projects that are considering condensed matter fusion approaches. And we're meeting with a NASA scientist tomorrow, which we'll record an entire podcast about. And I don't think that he's permitted to tell us the full story, but I think there are some people who perhaps realize that the way forward is different than the past.
But the other part of this is that it seems like there is like a weird culture of silence that's settled over the field, right? Where it's like there's anomalies in the way that data is being processed and the way that the LIGO project worked, the way that the images for the black holes were put together. And these are kind of like poorly kept secrets where when you ask the right questions, you start to discover that something isn't quite right, to the degree that even the people that are working on these projects internally are starting to realize it. And Steve, like, you've had direct experience with this, right?
That's true. The LIGO team reported that they detected gravitational waves, for instance, right? But it's quite ridiculous when you find out what the reality is, right? Because they never published a lot of things about their claims. And then they published things that were not true about their claims, right? So let's start with one that they published, which is not true about their claims. And then we'll come to the other one I said. So the first one is this. In their discovery paper, the LIGO team, it's a LIGO-Virgo collaboration, actually. So they claimed that they'd detected these two black holes colliding and they produced some black hole and some gravitational waves come flying off, right? And they say that they calibrated their machine. I call it another contraption because that's all it really is. And they said, well, we've calibrated it with our laser and all. Well, you try to get the calibration curve. Now, Dr. Wolfgang Engelhardt was a plasma physicist at the Max Planck Institute. I knew Wolfgang personally, right? I've had a number of conversations with him in Salzburg and in Munich on separate occasions, right? Unfortunately, he's deceased now. But all of this, what I'm telling you now, is still available on his webpage, which would be maintained by his colleagues and family. Right? And some of it's in German, some of it's in English, right? So he noted that, and he told me about this personally, right? So I got to know it from the horse's mouth, right? That there is no calibration curve. LIGO never had a calibration curve. The LIGO collaboration, they said LIGO-Virgo collaboration, I reckon, said that they did when in their original paper, right? And Wolfgang contacted a man named Professor Carsten Dansman, who's some bigwig, maybe the director of the Virgo aspect of it, right? And asked him for the calibration curve. Well, it never came. It got to the stage that legal action was contemplated to force them under German law and the freedom of information, etc., because it's public money that's funding these things, to produce the calibration curve. In the end, there was no calibration curve. They haven't got one.
So can we just break that down for people, what a calibration curve is and why it's important?
Well, it's lasers. In the LIGO machine, essentially it's a laser that's being bounced off of mirrors, right? And so you take a known laser input and you measure the output, right? And that can give you a calibration for your device, so that when you get any other signals coming in, you've got something you can compare it to and to see if it's a real or not, right? And to show that your device actually works. Right. So if you can't produce a calibration curve, you haven't proved your device can do anything.
So in other words, they have this system set up where they have some long, really long hallways where they have these lasers, right? And if there's disturbances in the hallway due to a truck going by or a gravitational wave, allegedly, it should alter the dimensions of the cavity, or the path of the laser, let's say, which will result in some phase interference as the laser is, remixed with itself through some mirror system, essentially, right? Is that a fair way of putting it?
More or less. Yeah, that's a simple way to put it, okay?
But you need to know what sorts of deflections would result from some standardized disturbance or something like that.
That's right.
And so if you don't have that, how do you calibrate the change that results, which is measured, versus what your expected change should be later on? And when you compare it to your library of possibilities for what it could be, something like that.
Yeah. Well, you got to remember that the range of deflections is in the attometer range. We're talking really, really tiny, right? And they claim that they've measured 1,000th of the diameter of a proton. Now, okay, well, where's your calibration curve to show that you can do that? Well, Engelhardt showed that they haven't got one. You can go to his webpage. As I said, this is just my word for it. Don't take my word for it. You can go to Wolfgang Engelhardt, right? And all the correspondence with Dansman and others is there. And you'll find that there is no calibration curve, right? So claiming that they've measured something 1,000th of the diameter of a proton, well, straight away you start to wonder about that one straight away, immediately. Yeah. But it gets worse. Not only have they got no calibration curve, they didn't publish. I'll come now to the things that they didn't publish. How did they do it with LIGO? Well, what they've done is this. At that time, they, using their general relativity theory and their own assumptions, etc., they wrote up a library. They call it of templates. They call it templates, but in reality, the templates are just calculated curves, just arbitrarily calculated curves. Well, not entirely arbitrary, because you set the parameters, right? We've got this kind of a black hole and that kind of a black hole. Well, whether you've got two black holes possible, that's another question. We'll just assume for the sake of argument that you can have two black holes, right? And you'll have a certain output of a black hole and gravitational waves. So they make a whole bunch of curves, because in the end, what comes out of their contraption is some curve that they plot. So they made a library of templates. What is a template? Well, it's just a curve that they made up themselves by calculations, and they put into the library. Now, what happens is they have what's called a generic noise. A generic noise, right? That's just some noise that comes out of the intestines of LIGO. And they take that noise, using computers, of course, and they try to find a curve of best fit in their library.
So is the generic noise the experimental output of the detector? That's what
right.
they call it?
What they say is a signal for a gravitational wave, right? They call it a generic noise. I kid you not, right? A generic noise. So they take the generic noise and they get their computers to go searching their library of templates, right, to find a curve of best fit. Well, it doesn't matter how many curves you've got there. You'll find some curve of best fit. It might be a reasonably good fit, or it's a pretty poor fit, but you'll find something because you can find the curve of best fit, and you take that out. Then whatever that curve of best fit was is what they say they detected. Okay? So how many curves of best fit did they have in their library of templates at the time they made they published their discovery paper of this first alleged LIGO detection? How many do you think? Do you know? Does anybody know?
I think it's quite a few.
Quite a few. Well, there's nothing published, but I know how many, and I've known for quite a long time, and I have the proof of it, right? They had 250,000. They made 250,000 curves by calculation using their computers and put it into a library. Then they get their generic noise, and they take that generic noise using those computers to find a curve of best fit in that library and say that generic noise is actually that one because, so they take that curve out and say, oh, what's that? Oh, well, it's that black hole and that black hole colliding to produce this kind of black hole and that much in the way of gravitational waves. So what do they get? Two black holes of certain masses, I forget exactly the numbers, 6 solar masses and 4 solar masses. I'm not quite, it's not that important because it's all rubbish. But then that combines to produce some black hole. What kind of a black hole? Well, according to Rightsey, it was a Kerr black hole. And now I know Rightsey, who was the director of LIGO at that time, says it's a Kerr black hole because he came to the University of Queensland, and I was asked by people I know in Queensland to go up there and confront Rightsey. So I sat up the front. I listened to Rightsey talking his spiel, and here's a funny thing. Before I go on to the other thing, here's a funny thing. Rightsey says, well, it's the theory of gravitation was developed in about 1643. And I was a bit perplexed by that. I thought, wow, that's very interesting. Does nobody in this audience have a problem with that statement? Why? Because Newton was born in 1642, and we're talking about Newtonian gravity. Now, Newton was a great genius, but I don't think he was when he was aged 1, right? So it goes downhill from there, right? So anyway, Rightsey tells me when I started questioning him, he says, oh, it's a Kerr black hole. When I never, and he tried to, it's just ridiculous, right? So anyway, that's a little side story.
By the way, it seems insignificant. Okay, so the guy didn't know anything about Newton, but it's kind of an endemic problem that scientists don't have the time in their careers to go back and understand how we came up with this just is illustrative of the fact that people don't actually have time to go back and look at where these ideas came from. That's really symptomatic of this wider effect. And at the end of the day, what makes this gravitational wave discussion relevant is that these very expensive experiments, these gravitational waves, are used ultimately for none other than justifying the gaseous model of the stars, because what do they detect? They detect these ultra-dense, compact, I don't even know if you can call them objects, these zero-dimensional masses, whatever. And the only way to achieve that is with a gaseous achieve it, in theory, is with a gaseous model of stars. And so they've kind of gone full circle by creating this very expensive device, which appears to lack calibration and seems to be something of a noise filter, to justify the conclusions of the gaseous model and pat themselves on the back, give each other prizes and say, oh, great, the stars are gaseous just like we thought all along. We can carry on and keep, playing with this idea.
Well, I think that it goes deeper than that too, because it's not just about the gaseous model of the sun, but it's also about the fact that the models that we have for the universe in general, for the cosmos, are so good that we can build a detector that's capable of this kind of noise floor. And I sometimes wonder if it isn't a pipe dream on some degree, that we're able to build something that's this complex to detect something that's so small from something that happens so far away, especially before we've even gotten to the point where we have a good model for the way that something much smaller and much simpler works, such as our own sun. And so it seems like the problem with LIGO or Virgo or or even CERN to some degree is that what we're doing is we are building these extraordinarily complex machines, but we haven't done the due diligence of demonstrating that the priors that have gone into building these machines that are kind of like monofunctional. It's not like you can convert LIGO to then do something else. Like it's a telescope with a single function. It's not a broad spectrum device. And so we've cemented the knowledge structures that go into it to say, well, we know this well enough to spend, billions of dollars on building this device, and whatever comes out of it, we have to interpret along those lines. And so it's not just reinterpreting the gaseous model of the stars. It's literally like
And reinforcing
we're reinforcing it. It's reinforcing like everything about the model. Because like you said earlier, how can you go back? You're stuck.
And the model is built on the foundation of this gaseous approach, which, again, just to kind of wrap this, just to like drive it home one more time, this is a 19th century conception that made sense maybe as the technological high point of that culture at the time. The thermodynamicists, the phase diagrams that they had recent access to, but it's super outdated. And honestly, it's time to move on. Like, the sun obviously has a surface. We got amateur astronomers on Twitter making incredible pictures of this liquid broth, spewing around the surface. How long can we stomach that it's just an optical illusion? How long can we stomach that an optical illusion is capable of containing the mass of the sun, right? I mean, enough is enough at some point. And if we want to move forward with our interpretation of what is going on when we look up at the sky, if we want to move forward with our energy production potentials here on Earth, let's call a spade a spade.
But I want to hear the end of this meeting. I think you're totally right about these things, but I want to hear the way that this meeting goes out. So you're in the audience, and he's presenting on these Kerr black holes.
Oh, that's right. So that's pretty well the end of the story there, because it didn't go anywhere. Raichi just in the end said to me, well, we'll just have to virtually agree to disagree. Really? That's not a scientific result, I don't think. But anyway, LIGO didn't detect anything really. All it did was it captured the irrational imagination of its operators. That's all it captured.
Something that was interesting in the story when you told it earlier was that you found that the people that you petitioned for details seemed like almost proud of the way that they had constructed the experiment. Because how did you get the calibration, the templates from them?
I was a little facetious in doing it. What I did was, when they made this announcement, and there was in an article that I read with the announcement, so not from the paper itself, from the announcement on a web page maybe, and it had some names of some people from the Virgo collaboration. So okay, here's an opportunity while they're drunk on their fame and fortune. I'll write to them, and I said, "This is a magnificent. What you've done here is fantastic." Right? Well, I was amazed. I said, "How did you do that?" Guy writes back, and he says, "Well, this is how we did it. We had these templates and blah blah blah." And I thought, templates? Well, what is that? And how many of them are there? So I wrote back. I said, thanks for the information. What's a template? And how many of them are there? He says, well, the template is these calculated curves, and we had 250,000 of them. I said, thank you very much. Right now, I've got those emails. I've kept all these emails. Right, it's evidence. Right, so if anybody wants to argue with me, say I'm not telling the truth. Yeah, sure. Let's go to court. I'll produce the evidence. Right. So, and I've often wondered then, because after the discovery paper, they claimed that they made further detections. We made this detection and that detection. Well, they've even quite of late. But and I wondered how many more templates have they made since they first started. Because what stops them making half a million, 1 million, 10 million? Right? It doesn't matter, because all it requires is the stamina of computer programmers. We'll just keep writing these things up and make more templates. Right? It's also like the detection of the M87 black hole. They used a similar process, except instead of calling their library elements, templates. They called them synthetic images, and they had a synthetic image library. Now, if you don't believe me, go and read their papers for the M87 alleged imaging of a black hole. Again, they didn't image anything except their wishful thinking. Now, with their model, they took a bunch of models, then they generated something like 64,000 synthetic images. Synthetic is another word for fake, right? I've got now 64,000 images, they say, in their database. Then they got this computer-generated noise. Then they got their computers to go and search their synthetic image database to find an image of best fit, but they didn't take the image out of their database. They kept the image their generic image that they generated with their computers, but they took the parameters of the image of best fit to claim that that's what they saw. So you tell me how they managed to find something out there when they never got out of their computers. It's a similar thing with LIGO. The whole thing is nothing but self-serving. It's self-serving. It tells you how far this kind of wishful thinking will go to satisfy the desired outcome. Now, it doesn't stop with them, because let's go back a few years, and they did the same with their Higgs boson, didn't they, with their Large Hadron Collider. I wrote a little article about that too, and explaining a few things about it long ago. It's somewhere on the internet. It's not a published paper. It's just floating around the internet somewhere. But this is how modern science has become. Great big teams spending huge sums of money, doing things that they don't tell anybody about, and making false claims, and then claiming that we've made great discoveries and keeping everybody happily employed, and the contractors in contracts. Because who's building, for instance, this giant contraption in France for the ITER project? It's a huge tokamak. The United States recently sent over this great big donut magnet, and the Chinese sent over some other giant component. Everybody's getting jobs and doing these things, yeah, but what's it for? It's for a pipe dream. Right? Now, when my paper was published on nuclear reactions in stars, I went and got all the email addresses of all the committee members of the 7 countries on the ITER webpage, and I sent them my paper. Guess what I got as a result of correspondence? Silence.
Yes, very little.
Silence. If you got up to $60 billion at stake on a fantasy, what are you going to do? Well, this now comes another question, doesn't it? This is not a science question. Now, this is a question of integrity and honesty. But when it comes to these sorts of things, it seems that integrity and honesty don't count for anything. Let's just keep quiet. Don't tell anybody. Maybe no one else will notice, and we'll go along, and we've got our cushy jobs or money or who knows what. I don't care.
Prestige, usually. Yeah.
Prestige,
it's
fame and fortune, because scientists are like any other person, right? In any other discipline, right? They have their own personal interests as well. And they want to make sure that their personal desires, like anybody else wants, are fulfilled. And more often than not, the truth becomes blurry, right? Because you've got vested interests. They've got their own interests involved. And that's the same with the academics at the university. Don't anybody ever tell you otherwise, right? And I'm sure you know from your own experiences that our educational institutions are driven more by fame and fortune than they are by scientific endeavor, right?
There's a few good soldiers left in the ranks.
There are a few good soldiers left, that's true. But where do the good soldiers end up if they stand up and speak? It takes courage to go up and speak, right? I've paid some prices for standing up and speaking, but that's part of the game. You've got to be prepared to take a cop on the chin once in a while, right? To tell the truth. But it seems to me that science has become a pretty sick joke at the moment. I don't know how long it will take before it's no longer a sick joke, but at the moment, it's a pretty sick joke. So we have to fix this problem for our younger generation of scientists, right? Otherwise, they'll spend their whole lives running down a garden path and achieve nothing in their scientific career. Right? So it's pretty bad if you get to the end of your scientific career and you find that you climbed up this great big ladder and you look over the hill or over the wall and you found you're on the wrong ladder.
Mm.
Right? So that's another aspect to consider in relation to all of this sort of thing, you know. But it's a
Do you
that's
run
the
into many
situation.
young scientists that are on this path, or do you find that there's just not really a trickle of people coming around yet?
I have not personally come across any academic young scientist who has approached me, for instance, about these issues over all the 20 more years that I've been involved. Not one. And I know of personally of various young scientists coming through, some of which I gave lectures to when they were in high school because of an invitation by the head teacher of their science, right? They've gone on to university and they've joined what? The club for career, reputation, and talk the same nonsensical theories, right? So the answer to that is no, I haven't seen any. But
That's
that doesn't mean there aren't any. There could be. And there probably are. But of course, they want to get their degree. When they're going to tell their professor, I'm sorry, professor, you don't know what you're talking about. You know, you're in violation of the laws of thermodynamics. You know?
That would be a hard
Yeah.
conversation.
It's like this guy, William Unruh. Now, William Unruh is the man for the Unruh effect, right? And my Dr. Pierre Robitaille and I wrote a paper some years ago now, not that long ago actually, and we covered the Unruh effect and Hawking's nonsensical temperature equation, which we've discussed earlier in this discussion. And so I sent it to a certain person, and I included Unruh in the correspondence because it was his theory that this certain person was involved with, right? So Unruh wrote back to me, and he was pretty terse, you know, and he says some silly things. I've got these emails too. So again, if anybody doesn't believe what I say and they want to see the evidence in a courtroom, for instance, I can produce it, right? So Unruh tried to claim this and that, and in the end, I showed no, you're in violation of the laws of thermodynamics. And I asked him, will you now see that this is a matter of scientific integrity? Will you tell anybody this? I haven't heard a word from him. So what's he doing about it? I don't know, but I certainly haven't heard nothing further, right? And anyway, what do you do? Bat on regardless. Yeah, that's what I say. Bat on regardless. In the end, I think that the truth will come out, but I'm sure that the current it's a pretty large clutch of scientists who have got all their interest vested in this nonsense will hope that it's long after they're gone, right? Because obviously they won't want their reputations and their fame and fortunes tarnished in any way by showing that they spent their whole lives on something that doesn't even exist. Yeah. Black holes, gaseous stars, neutron stars, and white dwarfs. None of this exists. Only the white dwarf exists in the sense that it's there, but it's not dwarf.
Maybe we'll see a culture of deathbed confessions from various scientists as they face down the end, where suddenly they admit to the fact that there's another way of doing
They've been
things.
looting the palace this whole time.
Yeah, exactly.
Yeah, I don't know. I think like our friend Jim's always talking about these institutional life cycles. It's like just these errors build up and people get really comfortable with looting the palace, and it just becomes the standard operating procedure. And sometimes things have to just break catastrophically before new approaches can rise up to replace them. And it seems tragic, but it's also just the cycle of history.
I also think that it's really exciting. Like I said earlier, if everything was really done and everything was figured out, I think that it's kind of a weird world to live in because you're born into a static universe where nothing will change. You'll inherit some collection of knowledge, and then what's the point of searching for new knowledge if everything is already known? And so I think that oftentimes these discussions end on this note of like, oh, well, this kind of sucks. Like everything is poorly fit together and gridlocked, and nobody knows that this needs to be redone. But I think that if there is more awareness that there's an entire world still to be discovered, that's actually very optimistic. And it pushes against the darkness of the day, which is that everything is done.
Well, that's a positive side, isn't it? On the positive side, there's a lot of work that can be done. People can go off now and see a golden opportunity to go and do some real scientific work and spend their lives doing something productive, satisfying, and for the betterment of the humanity and the scientific world, right? Because now we can cast aside all this nonsense and rubbish and get science back onto a track where it is actually a rational contemplation of nature rather than a totally irrational contemplation of nature. Well, if it's irrational contemplation, it's probably not natural. Anyway, so I look at the positive side. Well, we get rid of all of this rubbish. We can jettison it all because it's all rubbish. And now we've got a golden opportunity to do some real work. So anybody who's now starting out in science, if they take the lead now, you've been given the notice, take the lead, and then now you've got a chance to do something really important, really satisfying, really good. You're not stuck in a quagmire of putrefying nonsense, right?
Yeah, absolutely. What are you going to say, Shai?
I don't know. I don't think that's a good place to end. I think that a huge part of the puzzle for students coming into this is that the mysteries, the things we don't understand about the sky, have been given names as if they're solutions, right? Black holes, neutron stars, white dwarfs. They're treated like understandings, but they really cover up enormous misunderstandings. And so, like with my own students, I'm always trying to say, hey, when you see this word dark or black or whatever, something that seems super mystical in astronomy and astrophysics, that's an area that you should really put your imagination to and look into, because that's where all of the work is left to be done. And so I don't know. I think it's if you look at it the right way, I think there's a beautiful science to be developed still that, like you said, we thought we had crossed all the T's and dotted all the I's on, but it really couldn't be further from the truth.
This is a theme it's been around for quite a long time. Even Thomson, Lord Kelvin, right? William Thomson said just about at the turn of the 19th into the 20th century. So, well, we've discovered everything. All we've got to do is go a few decimal places, and it's complete nonsense. You've discovered everything. Well, have we discovered a lot more since then? Well, the engineers have done a good job. They've developed technologies and the technicians have done a good job. But certainly the astronomers haven't done a really bad job. And they're not the only ones, because there's a lot of other areas of science that has gone down the same sort of trail. So once we get rid of this rubbish, we can actually look forward to another era of enlightenment and learning, right? So this is something I think to be a takeaway here. We can learn a lesson from this, right? And don't waste your time on believing what you're told simply. Just think about things. As Leonardo da Vinci once said, anybody who argues from authority is not using his intelligence, only his memory, right? And so, don't just use your memory. Think about things. Don't necessarily believe what you're told. If you've got some reservations about what you're being told in school or at university or whatever it might be, don't bury them. Think about them, right? And you'll often find that your intuition will lead you to a better solution. Right? And who knows? You might even discover something yourself. And I've discovered nothing myself, right, other than mistakes by these astronomers and cosmologists and because I don't do theories, right? I don't have invent theories. I leave to other people with better abilities, right? So all I look at is, you've given me this. It comes back to thinking, right? You've given me this. You told me this. I want to think about that. Is that right? Well, that can't be right. Well, that can't be right. Well, there's 20,000 physicists who say it's right. Yeah, but there are 20,000 physicists who would just violate the first law of the zeroth law of thermodynamics, because you're making temperature non-intensive. It's probably more than 20,000 when you take all the physicists, the astronomers, the cosmologists. How many are there? But they're all out to lunch. They haven't come back. They're still out to lunch. Right? So, I think that the future's still bright for science, provided we go down the right trail and start accepting what reality is, and that the stars are not gases, they're condensed matter. You've got a good opportunity now of a new paradigm in astronomy, and this is a positive thing. But if people ignore that, well, you're going to waste your time, you're going to waste your life. I spent 20 years or more wasting my time, really. It's sort of a waste of time, but on one hand, but on the other hand, it's not a waste of time because someone's got to correct the mistakes. And if you don't correct the mistakes, then everybody else is going to follow this trail. So if now that mistakes are corrected, someone has to sacrifice some time and trouble to go and do it. Well, I've done some of it. Others have done some. Dr. Robitaille has done quite a lot. So now, with those corrected, other people don't have to waste their time doing that. You don't have to teach your students all this gaseous star business. You don't have to teach them all these twisted space-times with black holes and the like, right? And so why? It's a complete waste of intellect. It's a waste of your energy. Go and now look at something that's really serious.
I've found that if you just put the gaseous story next to the condensed matter story, for each one of these aspects, for the lives and deaths of stars, the students have a pretty easy time deciding which one makes the most sense.
Of course.
And it's quite an emotional journey usually for people because kids show up to my class really excited about these fantastical objects, right? They come in really excited to learn about black holes and time travel and all this stuff. But when they actually look at the record, the conclusions follow naturally from it. Yeah. So I don't know. I actually, this is freaking awesome. Sometimes I sit around and I'm like, this is going to make a hell of a story a few hundred years from now. I think that it's really profound to be seated here with you, to be, friends with Pierre and talking about these things and seeing this revolution unfold long before the world knows about it, right? But in every science book, they love the Galileo story. They love the story of the authority structures toppling under the weight of the rational evidence, right?
Yes.
This is going to be one of those stories. Okay. I don't know when.
Yeah. Well, I'd like to add a little story here as well, right? Now, this is a true story because I did it, right? So I know it's true. I know what I did, right? Now, let's go back to the CMB issue, right? In 1988, Professor Paris Harouni took a measurement of the CMB using the 54 2.6 optical radio telescope located in Armenia. It's probably it is in fact the most sensitive radio telescope ever built. It has an optical telescope with the radio antenna. So this is with the radio antenna. Now, it's designed by Professor Harouni. He's now deceased, unfortunately. And it's effectively what he calls himself an antenna without edges. What does he mean? It's so designed that diffraction of microwaves from the surroundings that do not enter the detector. So he's eliminated that problem, right? Now, the self-noise of the radio antenna is about 2.8 Kelvin. So what's the so-called alleged CMB temperature? 2.715, something like that. Pretty well 2.8, right? He now takes a sample of the cosmos, and what does the antenna return? 2.8. So that means there's one of two things. The self-noise of the antenna is actually zero, which is impossible, right? And that 2.8 is a relic of the Big Bang, or the 2.8 is the self-noise of the antenna, and it's zero for the CMB. Well, that's the real one because the first one is impossible. They can't have zero noise for the self-noise for the antenna. So that means that's a direct measurement that the CMB does not exist. Well, we know that the CMB has not been detected at L2, and this measurement by Professor Harouni on Earth using this radio telescope proves it too. Right? Now, Professor Harouni wrote 2 papers, one of which was published in a meeting in the UK on radio antennas. The other one was published in the Journal of Applied Electromagnetism in, I think they're headquartered in Athens, Greece, right? Now, I went looking for the paper, and it's not on the archive of it was not on the electronic archive of that journal. So I contacted Professor Harouni's colleagues in Armenia and asked them for a copy of the paper. I knew of its existence. They went to their laboratory library and got a copy of it and sent it to me. I then went to the then current editor of the Journal of Applied Electromagnetism. And I said, well, where's this paper? He said, I've never heard of it. I said, well, I've got a copy of it. Here it is. He was astonished. He had never seen it, never heard of it at all. He then contacted the former editor, who, after a little while, admitted that there was a paper. Well, he couldn't say otherwise. I got a copy of the thing. And anyway, ultimately, the paper was reinstated on the electronic archive. Why was it missing in the first place? Well, according to the former editor, it was a clerical mistake. Clerical mistake. Yeah, well, perhaps pigs do fly, but I don't think it was a clerical mistake. Now, that paper is now available. You can go to that webpage because they make their archive available free. And so I've checked it recently. It's still there now, because you never know with these vested interests what will disappear. Well, that disappeared. Now it's reinstated. Right? So you can go and get that paper and have a read of it. It's a short paper. It's got its elements of the design of the telescope and the radio telescope as well, and Dr. Haruni's or Professor Haruni's calculations in showing it, and it's a definitive measurement. Now compare that to the Kobe-Furious measurement. The Kobe-Furious measurement was a joke. This measurement is not a joke, but no one talks about it. Have you seen any cosmologist talk about the radio telescope in Armenia and what it measured? Silence, right? Everything now is Kobe-Furious. It's always Kobe-Furious. Well, Dr. Roberto has shown that the Kobe-Furious measurements is actually a detection of microwave emission from the oceans, which diffracted over the shield of the Furious instrument into the detector. Now, if you go and have a look, as I have done and a number of other people have done, at the engineering specifications for the shield of Kobe, you will find that it was incapable of preventing microwave diffraction over the shield. That's it.
Pierre's done really incredible work in taking apart all of these various measurements, and we've talked to him extensively about it. We talked to him when we were talking with Jim and him most recently. And I think that all of this tells the story of how incomplete the picture is. And so there's so much that's left.
And really to what lengths people will go to defend inherited wisdom too, which may be false in some sense, or broken or incomplete or outdated. I mean, people bend over backwards to the extent of removing articles from the record, you know?
Yeah. I mean, I think the Haruni antenna is a really tragic story, right? Because it fell into disrepair. Now it's decommissioned. It's in ruins. His daughter is trying to bring up the funds.
It's his niece.
His niece. I didn't realize that. His niece is trying to bring up the funds to be able to bring it back online, but obviously this is a huge endeavor for a country that doesn't have an enormous science program, and so it's unclear if it'll ever come back online to be able to redo the measurement. And when we were at the conference, there was actually a lot of, Aziz presented a really interesting theory about possible sources of the cosmic microwave background that predate any antenna measurement. Right? So it's like there's this long history of the steady state universe theorists trying to figure out if there was a background temperature to space. And so it's been really interesting talking to Pierre in the aftermath of all of these discussions, because he's slowly starting to consider that there may be extraterrestrial water-based sources for the CMB, like ice clouds and various molecular sources of water that are in outer space.
We are getting so far beyond the scope of this conversation. I mean, I love this stuff, but we've almost done 3 hours at this, and I feel like cracking open the CMB in the last 5 minutes of this podcast is just not going to do it justice.
It's true, but we are going to release the conversation with Aziz, and we'll have other conversations about it. And so I think I wanted to wrap on this idea that it's still alive. The questions aren't solved. And Pierre's done incredible work on all of this. And the Haruni antenna is an interesting piece of it. But you're right, that we can't finish it in 5 minutes and wrap on it. But I think that it's a really interesting thread from which to pull further discussions, which is the fact that, yes, there's mathematical problems with the way that the thermodynamics has been applied to the gaseous model of the stars. But it doesn't end with the stars. It goes into the CMB. It goes into the design of these instruments, the structure of these projects. It's like, it's such a fascinating and limitless world that opens. And so I guess what I'm trying to say is that I hope that the takeaway from this is not that everything is broken, but that the takeaway is that there's so much that is still left to be discovered, to be done. And that, Steve, you've been such an instrumental figure in making this clear to people. And I'm really grateful for the fact that you came to visit and that you've spent so much time in discussion with us about these ideas and all the work that you've done.
Well, thank you very much for the invitation and giving me the opportunity to say a few things and maybe make a few jokes. I like to make a few jokes, as my videos sometimes show, because I figure if you can't be jovial about the whole thing, you'll go crazy with this nonsense, right? So we have to laugh at it all and keep them in perspective so we can do something real.
Absolutely. Any closing thoughts, Shiloh?
I mean, we're human. We learn by making mistakes. I think that this will be tremendously instructive in the history of the world as it plays out the history of science. And I think all of the ways in which modern astronomy has been misled, whether it's the filtering of noise or the misapplication of outdated concepts from eras of experimental inadequacy, all of these things will be landmines to avoid in the future. And that's just how it goes as a human being. You screw things up, and hopefully you have the humility at some point to reckon with how you've gone wrong and fix it in the future. And generally, that's how we move forward.